Something impossible is drifting through our solar system right now, and it's bleeding metal into the void of space. Comet 3I Atlas is racing past the Sun at over 200,000 kilometers per hour, trailing a cloud of vaporized nickel that shouldn't exist. Not here. Not at this distance. Not under these conditions. The laws of thermodynamics say that metals don't vaporize this far from a star. The temperature is far too cold, and yet instruments around the world have detected unmistakable signatures of nickel gas streaming from this ancient visitor, glowing in wavelengths that reveal a chemistry that defies our understanding of how matter behaves in deep space. This is the third interstellar object ever confirmed passing through our cosmic neighbourhood. And it's the strangest one yet. If you enjoy uncovering the universe's most disturbing secrets, hit that like button. Because what you're about to discover will change how you think about the space between stars forever. We're not alone in the galaxy, but what's out there in the dark might be far more alien than you ever imagined. We begin. On July 1st, 2025, a telescope in the Chilean desert detected a faint smudge of light moving against the background stars. The Atlas survey system, designed to scan for asteroids that might threaten Earth, flagged the object as unusual. Its trajectory was wrong. The angle was too steep. The velocity was too high. Within hours, astronomers around the world turned their instruments toward this mysterious visitor, and what they found shouldn't be possible. The object was following a hyperbolic orbit, not an ellipse, not a parabola. A hyperbola. This means its path is open-ended, not gravitationally bound to our Sun. It came from interstellar space, and it will return to interstellar space, moving too fast for our star's gravity to capture it. When scientists traced its trajectory backward through time, they discovered something that made the hair stand up on the back of their necks. This object originated from somewhere else in the galaxy, from a star system so distant that we may never know which one. They named it 3I Atlas, the third interstellar object, and from the moment of its discovery, nothing about it has made sense. The first hint of its impossible nature came when researchers at the Very Large Telescope in Chile pointed their spectrographs toward the visitor. They were looking for the chemical signatures that would reveal what this ancient wanderer was made of. What they found was nickel vapor. Not trace amounts, not faint hints. Strong, unmistakable emissions of vaporized metal streaming from the comet's nucleus into the surrounding space. This discovery sent shockwaves through the astronomical community. Nickel doesn't vaporize at the temperatures that exist nearly 4 times Earth's distance from the Sun. The thermal energy required to turn solid metal into gas simply doesn't exist that far out in the solar system, and yet, day after day, observation after observation, the nickel signature remained. It even grew stronger as the comet continued its journey toward the Sun, as if the object was bleeding metal into space through some process that our physics can't explain. The researchers who made the discovery described the moment with barely contained excitement. It was pretty clear that it was nickel, said Thomas Puzia, who led the team at the Instituto de Astrofísica in Chile. So it was super exciting. But underneath that excitement lies a deeper unease. If nickel can vaporize under conditions where it should remain solid, what else about our understanding of matter and energy in space is fundamentally wrong? The mystery deepens when you look at the comet's other properties. James Webb Space Telescope observations revealed that 3I Atlas is dominated by carbon dioxide rather than water vapor. Most comets from our solar system are primarily water ice, with smaller amounts of other volatiles mixed in. But this interstellar visitor is different. Its coma, the cloud of gas and dust surrounding its solid nucleus, shows massive concentrations of carbon dioxide sublimating directly from solid to gas as the comet warms. This carbon dioxide dominance tells us something profound about where 3I Atlas came from. It formed in a stellar environment chemically different from our Sun's protoplanetary disk. The star system that gave birth to this object had different abundances of elements, different temperatures, different conditions during planet formation. This comet is a chemical fingerprint from another world, carrying the signature of stellar processes that unfolded billions of years ago around a sun we may never identify. Hubble Space Telescope images captured on July 21st show a teardrop-shaped cocoon of dust streaming from the comet's nucleus. The size estimates vary wildly because the object is so far away and so unusual. Some measurements suggest a nucleus as small as 440 meters across. Others indicate it could be as large as 5.6 kilometers in diameter. This uncertainty itself is unsettling. We're looking directly at an object with some of humanity's most powerful telescopes, and we still can't agree on how big it is. But size is just the beginning of the anomalies. The comet exhibits what astronomers call extreme negative polarization. When light reflects off the dust particles in 3I Atlas's coma, it becomes polarized in a way that doesn't match any known comet or asteroid in our solar system. The polarization measurements show a deep, narrow negative branch that reaches negative 2.7% at a phase angle of 7 degrees. These numbers mean nothing to most people, but to astronomers studying the optical properties of small bodies, they represent something unprecedented. Every comet we've ever observed polarizes light in predictable ways based on the size, shape, and composition of its dust grains. 3I Atlas breaks all those patterns. Its polarization signature resembles rare F-type asteroids and cometary nuclei more than active comets. This suggests that either the dust particles in its coma have a completely different structure from normal cometary dust, or the object itself is something other than what we call a comet, a hybrid, a transitional object, something that doesn't fit into our taxonomic categories because it formed under conditions that don't exist in our solar system. The comet's colour adds another layer of strangeness. Observations show a distinctly reddish hue caused by organic compounds called tholins that have been irradiated by cosmic rays during the object's billions of years wandering through interstellar space. This redness evolved and deepened throughout July 2025 as the comet's activity increased, indicating that the surface composition is changing as fresh material sublimates and exposes deeper layers that have been chemically altered by radiation. Think about what that means. This object has been drifting through the galaxy for so long that cosmic radiation has fundamentally transformed its surface chemistry. The outer layers have been cooked by high-energy particles, creating complex organic molecules that give the comet its blood-red colour. Underneath that irradiated crust lies material that has remained frozen and unchanged since the comet's formation, potentially billions of years ago. Preliminary age estimates suggest 3I Atlas is between 3 billion and 11 billion years old. Our solar system, for reference, is 4.6 billion years old. This means the comet could have formed when the universe was less than half its current age, in a galactic environment radically different from today. Star formation rates were higher, heavy element abundances were lower, the chemistry of planet formation operated under different rules. This ancient visitor is a messenger from that primordial epoch, carrying information about stellar and planetary processes from an era we can never directly observe. The fact that it's dominated by carbon dioxide is particularly significant. CO2 sublimates directly from solid to gas much more easily than water ice. This high volatility suggests something remarkable. 3I Atlas has likely never been close to another star before its current passage by our Sun. If it had, the thermal energy from that earlier stellar encounter would have boiled away most or all of its carbon dioxide, leaving behind less volatile compounds. The presence of so much CO2 means this is probably the comet's first close approach to any star in billions of years. Imagine that. An object that formed around an ancient star was ejected into interstellar space billions of years ago and has been wandering through the cold dark between stars ever since, never coming close enough to another sun to wake from its frozen sleep. Until now. until it happened to pass through our tiny corner of the galaxy and encounter our Sun purely by chance. The statistical improbability of this event is staggering. Our solar system occupies a minuscule fraction of galactic space. The odds of an interstellar object randomly passing through our neighbourhood are astronomically small, and yet, in just 8 years, humanity has now detected 3 confirmed interstellar visitors. 3 objects from the space between stars that happen to pass close enough for us to observe them. This raises a question that makes astronomers deeply uncomfortable. If we've detected 3 interstellar objects in less than a decade of serious searching, how many are we missing? Statistical models suggest that dozens or even hundreds of these cosmic wanderers should be passing through the inner solar system at any given moment, most of them too small or too dark or moving at angles that make detection impossible with current technology. We are swimming in debris from dead star systems. Fragments of destroyed worlds drift through our cosmic neighbourhood constantly, carrying the chemical signatures of stellar environments we'll never see. Most pass by unnoticed, invisible messengers from the deep galaxy that enter our space and leave without acknowledgement. 3I Atlas is one of the lucky ones. We saw it. We studied it. But it represents just a tiny fraction of the interstellar material constantly flowing through the solar system. The comet made its closest approach to the Sun on October 30th, 2025, coming within 126 million miles of our star, just inside the orbit of Mars. Ground-based telescopes lost sight of it temporarily as it passed behind the Sun from Earth's perspective, but space-based observatories, including the Solar and Heliospheric Observatory and the Punch mission, continued tracking it throughout its perihelion passage. This was the moment astronomers had been waiting for. As 3I Atlas swung around the Sun, the intense solar radiation would heat its nucleus, causing more material to sublimate, potentially revealing new chemical signatures that could tell us more about its composition and origin. And the observations did not disappoint. The nickel vapor emissions intensified. The carbon dioxide production increased dramatically. The comet brightened unexpectedly, suggesting that fresh material was being exposed as the outer layers burned away. But the anticipated fragmentation never occurred. Some scientists had predicted that the thermal and tidal stresses of perihelion might break the comet apart, as happened with the previous interstellar visitor, 2I Borisov. But 3I Atlas held together, its nucleus remaining intact even as it shed massive amounts of material into space. This structural integrity tells us something about how it's put together. The object is either more cohesive than typical comets, or its nucleus is larger and more massive than the observations suggest, giving it enough gravitational self-attraction to resist tidal disruption. The comet is currently moving away from the Sun, heading back toward interstellar space on its open hyperbolic trajectory. Within a few years, it will cross the outer boundaries of the solar system and return to the dark ocean between stars, where it will drift for millions or billions of years before potentially encountering another stellar system. We will never see it again. This one passage, these few months of observation, represent our only opportunity to study this particular messenger from the ancient galaxy. Every measurement matters, every spectrum, every image, every data point is irreplaceable, because once 3I Atlas leaves, it's gone forever, carrying its secrets back into the cosmic void. But here's what makes this story truly unsettling. 3I Atlas is not humanity's first encounter with an interstellar visitor, it's the third. And when you examine all 3 objects together, a disturbing pattern emerges. Each one is radically different from the others. Each one violates our expectations in completely unexpected ways. And collectively, they suggest that the space between stars is far more complex, far more dangerous, and far more alien than our models of galactic chemistry and dynamics ever predicted. To understand why 3I Atlas is so disturbing, you need to know about the 2 visitors that came before it. Because the pattern they reveal together is one of the most unsettling discoveries in modern astronomy. On October 19, 2017, astronomers at the Pan-STARRS telescope in Hawaii detected something impossible. An object was moving through the inner solar system on a trajectory that made no sense. Its orbit was too eccentric. Its velocity was too high. Within days, scientists confirmed what the data suggested. This was not an asteroid from our solar system. It had come from interstellar space. They named it Oumuamua, a Hawaiian word meaning scout, or messenger from afar arriving first. And from the beginning, nothing about it fit our understanding of what interstellar objects should look like. Oumuamua was dark, extremely dark. Its surface reflected only about 4% of the light that hit it, making it one of the dimmest objects ever observed. This darkness suggested a surface composition unlike any asteroid or comet in our solar system, potentially carbon-rich materials or organic compounds that had been radiation processed during billions of years in interstellar space. But the real shock came when scientists tried to determine its shape. Based on how its brightness varied as it tumbled through space, astronomers calculated that Oumuamua must be extremely elongated, possibly 10 times longer than it was wide. Some estimates suggested a cigar or needle shape up to 400 meters long, but only 40 meters wide. This aspect ratio is completely unprecedented among natural solar system bodies. Nothing we've ever observed has that extreme elongation. The weirdness continued. As Oumuamua sped away from the sun, something unexpected happened. It accelerated. Not much. Just a tiny fraction of a percent faster than gravity alone could account for. But that's small. Deviation was enough to break the laws of orbital mechanics as we understand them. When comets accelerate as they leave the sun, it's because they're outgassing volatile materials that create a rocket effect, pushing them off their gravitational trajectory. But here's the problem. Oumuamua showed no visible coma, no tail, no signs of the outgassing that would be needed to explain its non-gravitational acceleration. It was acting like a comet, but looking like an asteroid. An impossible combination. Scientists proposed numerous explanations. Maybe it was outgassing something invisible like hydrogen or nitrogen. Maybe its spin state was changing, creating subtle forces through the Yorp effect. Maybe it was covered in some exotic material that reflected sunlight asymmetrically, creating radiation pressure that pushed it off course. Every explanation had problems. Every model left something unexplained. And then came the truly disturbing suggestion. What if Oumuamua wasn't natural at all? Harvard astronomer Avi Loeb proposed that the object's extreme elongation and non-gravitational acceleration could be explained if it was an artificial light sail, a probe sent by an extraterrestrial civilization to explore the galaxy. A thin, reflective sheet would have exactly the right properties to match Oumuamua's observations. It would be highly elongated, extremely thin, dark on one side, accelerated by radiation pressure, and show no outgassing because it wasn't made of ice and rock at all. The scientific community largely rejected this hypothesis, arguing that extraordinary claims require extraordinary evidence, and that natural explanations, while imperfect, were more plausible than invoking alien technology. But Loeb's suggestion highlighted something important. Oumuamua was so weird, so unlike anything we'd ever seen that even the alien hypothesis couldn't be completely ruled out based on the available data. Oumuamua disappeared into the depths of space, leaving behind more questions than answers. Was it a comet with unusual properties? An asteroid unlike any in our solar system? A piece of planetary debris from a catastrophic collision in another star system? Or something else entirely? We will never know. Our telescopes lost sight of it before we could gather enough data to definitively answer those questions. But Oumuamua taught us a crucial lesson. Interstellar objects don't have to resemble anything from our solar system. They can come from stellar environments with completely different formation conditions, different chemical abundances, different planetary system architectures. The galaxy is not uniform. Different stars create different types of worlds, and when those worlds are destroyed, the fragments they scatter into interstellar space can be profoundly alien. Then, on August 30th, 2019, humanity encountered its second confirmed interstellar visitor. And this one was completely different. Crimean amateur astronomer Gennady Borisov was searching the sky with his homemade 65cm telescope when he spotted a faint comet moving through the constellation of Gemini. Follow-up observations confirmed its interstellar origin. The orbit was hyperbolic. The trajectory clearly indicated the object had come from outside the solar system. They designated it 2I Borisov, the second interstellar object, and telescopes around the world scrambled to observe it before it completed its swing around the Sun and departed back into the void. 2I Borisov was a relief. Finally, an interstellar visitor that made sense. It looked like a comet. It behaved like a comet. It had a visible coma and tail. It outgassed normally. Its spectrum showed water vapour, carbon monoxide and cyanide compounds typical of comets from our solar system. Scientists could apply their normal comet analysis tools, and the results came back reassuringly familiar. But that familiarity was deceptive, because when researchers looked closer, they discovered that 2I Borisov, while comet-like, was still distinctly alien. The carbon monoxide abundance was unusually high compared to typical solar system comets. Spectroscopic observations revealed CO concentrations suggesting that Borisov formed in an extremely cold environment, possibly around a red dwarf star with far less luminosity than our Sun. The high carbon monoxide content indicated that the comet's ices condensed at temperatures lower than those found in our solar system's formation disk. The comet's dust properties were also unusual. Polarization measurements showed that Borisov produced unusually high positive polarization, different from most solar system comets, but similar to a rare class of comets that includes the famous Hale-Bopp. This suggested that its dust grains had different compositions or structures than typical cometary dust, possibly due to formation in a chemically distinct protoplanetary disk. And then came the fragmentation. In March 2020, as 2I Borisov moved away from the Sun, it began to break apart. Hubble images captured the nucleus splitting into at least two distinct pieces, with a debris field of smaller fragments trailing behind. This breakup was both expected and revealing. Expected because cometary nuclei are fragile, weakly bound rubble piles that can't always withstand the thermal stress of solar passage. Revealing because the way Borisov fragmented provided clues about its internal structure and strength. The comet's destruction raised an uncomfortable question. If an interstellar object survives billions of years wandering through the galaxy, only to break apart during its first close stellar encounter, how many interstellar visitors self-destruct before we can study them? How many fragments of destroyed worlds pass through our neighbourhood, briefly visible as they disintegrate, then vanish as clouds of dissipating debris? But despite its unusual properties, 2I Borisov was fundamentally recognisable. It was a comet. Strange, yes. From another star system, certainly. But its behaviour fit within the extended range of cometary phenomena we'd already documented. It confirmed that at least some interstellar objects are similar to what we find in our own solar system, just with subtle chemical and physical differences reflecting their exotic origins. This made scientists cautiously optimistic. Maybe Oumuamua was the anomaly. Maybe most interstellar visitors would resemble familiar solar system objects with minor variations. Maybe the space between stars wasn't so alien after all. And then came 3I Atlas. And that optimism died. Now we have 3 confirmed interstellar objects, 3 messengers from the deep galaxy. And when you compare them side by side, the pattern is terrifying. Oumuamua. Dark, elongated, accelerating without visible outgassing. Possibly rocky or metallic or something we can't classify. Tumbling chaotically. No coma, no tail, no comet-like behaviour despite showing non-gravitational acceleration. 2I Borisov. Active comet with high carbon monoxide. Visible coma and tail, normal outgassing, fragmented during solar passage, recognisably comet-like, but with unusual chemical abundances. 3I Atlas, active comet dominated by carbon dioxide instead of water, vaporizing nickel at impossible temperatures, extreme negative polarization unlike any known object, reddish organic rich surface, holding together structurally despite perihelion stress. 3 visitors, 3 completely different types of objects, 3 sets of properties that don't match each other or anything from our solar system. This is the pattern that keeps astronomers awake at night. We're not seeing variations on a theme, we're seeing fundamental diversity. Every interstellar object we detect is radically different from the last. There is no template, no standard interstellar visitor profile. Each one represents conditions, processes, and environments that are completely unique. And that raises the most disturbing question of all. If the first 3 interstellar objects are this different from each other, what will the 4th one look like? The 10th? The 100th? How many categories of cosmic debris are drifting through the galaxy? How many types of failed worlds, destroyed planets, and stellar system fragments are we going to encounter as our detection capabilities improve? The diversity itself is the terrifying revelation. It suggests that planetary system formation and destruction throughout the galaxy produces outcomes far more varied than our solar system sample size of 1 could ever prepare us for. We thought we understood how planets form, how comets condense, how stellar systems evolve. But we based those theories on observations of our Sun and its family of worlds. We didn't account for the possibility that different stellar environments might create completely alien outcomes. Red dwarf systems might produce comets with bizarre chemical compositions. Binary star systems might eject objects with properties we've never imagined. Super-Earth planets might have moons that, when gravitationally scattered, become interstellar wanderers unlike anything in our asteroid belt or Kuiper belt. The galaxy is a laboratory of planetary formation scenarios, and the debris field from 13 billion years of stellar evolution is far more complex than we ever anticipated. Statistical analyses based on the 3 confirmed interstellar detections suggest that between 1 and 10 interstellar objects larger than 100 meters in diameter pass within Neptune's orbit every year. Most go undetected because they're small, dark, or moving at angles that make them difficult to spot against the background stars. But they're there, constantly streaming through our neighbourhood, fragments of distant disasters carrying information about worlds we'll never visit. The Vera C. Rubin Observatory, scheduled to begin full operation soon, will revolutionise interstellar object detection. Its wide-field survey capability will catch fainter, faster-moving targets that current systems miss. Conservative estimates suggest Rubin could detect dozens of interstellar visitors per year. Optimistic projections go into the hundreds. Think about what that means. Within the next decade, we might catalogue more interstellar objects than exist in some asteroid families. We'll have samples from stellar systems across a significant volume of the galaxy. We'll see debris from red dwarfs, yellow stars like our Sun, massive blue giants, and ancient stars that formed when the Milky Way was young. Each object will tell a different story. Each one will reveal new possibilities for how matter can organise itself around alien suns. But this coming flood of data also means we'll encounter more mysteries, more impossible compositions, more objects that violate our physical expectations, more reminders that the universe operates according to principles we're only beginning to glimpse. And here's what might be most unsettling. We're already seeing patterns in the 3 objects we've detected, not similarities, patterns of difference. Oumuamua accelerated mysteriously. 3I Atlas vaporizes metal impossibly. Each violation of expectations is unique, but the consistency of anomalousness itself is a pattern. It suggests that interstellar objects routinely exhibit properties that shouldn't exist, according to our understanding of physics and chemistry. This pattern of consistent weirdness has implications for how we think about the galaxy itself. If the normal baseline for interstellar debris includes objects that defy our models, then perhaps our models are the problem. Perhaps we've built theories of planetary formation and stellar evolution based on too limited a sample. Perhaps the physics of how matter behaves in extreme environments needs fundamental revision. Or perhaps the galaxy is simply stranger than our Earth-based experience prepared us to comprehend. The 3 interstellar visitors also tell us something profound about galactic recycling. Matter doesn't just orbit stars forever. Planetary systems are dynamic, violent environments where gravitational interactions constantly shuffle objects into new orbits. Some get ejected entirely, flung into interstellar space by close encounters with massive planets. Once in the galactic environment, these orphaned objects travel for millions or billions of years, crossing vast distances, potentially passing through multiple stellar systems before either being captured by another star's gravity or continuing to wander indefinitely. 3I Atlas, based on its trajectory, likely originated from somewhere in the galactic thick disk, a region of ancient stars that formed billions of years ago. Its old age fits this origin. The thick disk contains stars from an earlier epoch of galactic evolution, when metallicity was lower and formation conditions were different. A comet from such an ancient source would be expected to have unusual composition reflecting the primordial chemistry of the young galaxy. But here's the unsettling part. That comet has been wandering for billions of years. It has drifted through regions of space we'll never observe, past near stars that may no longer exist, witnessed stellar processes and galactic evolution across time spans that dwarf human history. It is an archaeological artifact from an era we can only theorize about, and it's currently moving through our solar system purely by chance. And when it leaves, it will carry its secrets away with it. The detailed composition of its nucleus, the structure of its interior, the precise catalogue of volatile compounds locked in its ices. We're gathering what data we can, but there's only so much you can learn from millions of miles away using spectroscopy and imaging. The truly complete analysis would require a spacecraft rendezvous, sample collection, detailed in situ measurements. But 3I Atlas is moving too fast. We detected it too late. By the time we could design, build and launch an intercept mission, the comet would already be gone billions of miles away and accelerating. The same was true for Oumuamua and Borisov. We saw them, we studied them from afar, and then we lost them. Every interstellar visitor follows this pattern. Brief detection, frantic observation, permanent departure. We live in a shooting gallery of cosmic debris, and we're perpetually too slow to catch the objects flying past. This might change. Engineers have proposed rapid response mission concepts specifically designed to chase down interstellar intruders. Small, pre-built spacecraft that could be launched within weeks of a new detection, reaching the target while it's still within range for detailed study. The technology exists, the designs are feasible. What's missing is the funding and political will to keep such missions on standby. But even if we develop that capability, we'll face a more fundamental problem. These objects are alien, not metaphorically. Literally alien. They formed under conditions that don't exist in our solar system, around stars with different properties than our Sun, in protoplanetary disks with different chemistries. When we send missions to asteroids or comets from our solar system, we're studying materials that formed in a familiar environment. We can predict what we'll find because we understand the formation context. Interstellar objects remove that safety net. We have no idea what processes created them. We don't know what their parent stellar systems looked like. We can't predict what exotic minerals or organic compounds might exist in their structure. When we eventually send a spacecraft to rendezvous with an interstellar visitor, we'll be making first contact with matter from another stellar environment, and there's no guarantee that matter will behave the way we expect. The nickel vapor around 3I Atlas is a perfect example. Metals shouldn't vaporize at those temperatures, but they do. Something about this object's composition or structure, allows nickel to sublimate under conditions where it should remain solid? Is it mixed with more volatile compounds that carry it away during outgassing? Is the nickel in some unusual chemical state that lowers its sublimation point? Is there an exotic process we haven't discovered that can vaporize metals through non-thermal mechanisms? We don't know. And the fact that we don't know is the point. These objects surprise us, they violate our expectations, and each violation is a reminder that the universe is under no obligation to conform to theories built from observations of one solar system around one ordinary star. The comparison between the three interstellar visitors also reveals something about the violence of galactic dynamics. All three objects were ejected from their home systems. Something catastrophic happened to tear them away from the stars they originally orbited. For most interstellar objects, that something is probably gravitational scattering by large planets during the chaotic early phases of stellar system formation. Jupiter-mass worlds shuffling smaller bodies into increasingly elliptical orbits until some cross the threshold velocity needed to escape entirely. But some interstellar debris might have more violent origins: stellar collisions, supernova explosions, close encounters between binary stars that gravitationally shred entire planetary systems. When a star dies in a supernova, it doesn't just destroy itself, it obliterates or ejects everything orbiting it. Planets are vaporized or blown into interstellar space at tremendous velocities. Comets and asteroids are scattered like shrapnel from an explosion, each fragment carrying the chemical signature of the stellar cataclysm that created it. Could any of our three interstellar visitors be survivors of such violence? Could Oumuamua be a fragment of a world destroyed when its star exploded? Could 3I Atlas be debris from a planetary system torn apart by a stellar collision? We can't know for certain, but the possibility adds another layer of darkness to these objects. They're not just messengers from distant systems. They might be tombstones, markers of stellar death and planetary destruction, evidence of cosmic catastrophes that occurred billions of years ago in regions of the galaxy we'll never observe. And they're everywhere. The space between stars is filled with the wreckage of destroyed worlds, dead comets, shattered asteroids, planetary fragments, all drifting through the galactic void, occasionally passing through living stellar systems like ghosts haunting someone else's house. Our solar system is just one stop on their endless journey through the dark. This realization fundamentally changes how we think about galactic space. It's not empty. It's not a sterile void. It's an ocean of debris, a cosmic scrapyard where the remains of billions of years of planetary formation and destruction drift in slow, patient orbits around the galactic center. Some of that debris will eventually be captured by other stars, incorporated into new planetary systems, recycled into new worlds. But most will wander forever, eternal nomads carrying their secrets through the endless night. And here's the truly unsettling thought. If our solar system is constantly bombarded by debris from dead stellar systems, what happens when our sun dies? When the sun expands into a red giant billions of years from now, it will destroy Mercury, Venus, and possibly Earth. Mars might survive in a wider orbit, but the inner solar system will be consumed by our expanding star. And when that happens, objects from the outer solar system will be gravitationally perturbed, scattered into new orbits, some of them ejected into interstellar space. Billions of years from now, fragments of our world might be drifting through another star's planetary system. Future astronomers around distant suns might detect objects labelled 4I or 27I that originated from our solar system's death throes. They might observe weird chemical signatures that reflect Earth's biosphere, or Mars's minerals, or Jupiter's atmospheric composition frozen into cometary ices. They might wonder what kind of stellar environment created such strange visitors. And they'll never know that those fragments once orbited a star that sheltered a world where life evolved and built civilizations and stared up at the night sky, wondering if they were alone. This is the cycle. Stars are born, planets form, systems mature, eventually catastrophe strikes, stellar death, gravitational chaos, cosmic collision. The system breaks apart. Fragments scatter into interstellar space. Those fragments drift through the galaxy for millions or billions of years. Some encounter new stellar systems. A tiny fraction get detected by astronomers before continuing their journey. And the cycle continues. We are not separate from this process. We are participants in it. Right. Now, as you read these words, fragments of dead worlds are passing through our solar system. Objects that once orbited living stars carrying matter that may have been part of alien worlds are streaming past us, invisible, undetected, but present. And someday, when our sun dies and our world is destroyed, fragments of Earth will join that cosmic diaspora, wandering through the galaxy forever. The 3 interstellar visitors we've detected are just the beginning of humanity's relationship with this galactic debris field. As our detection technology improves, we'll find more, many more. The statistical models suggest we're missing 90% or more of the interstellar objects that pass through the inner solar system. We're seeing the brightest, the closest, the ones that happen to be oriented favourably when we're looking in the right direction. We're missing all the small ones, the dark ones, the ones moving too fast or at inconvenient angles. But even with our current limited capabilities, the pattern is clear. The first 3 interstellar objects are wildly different from each other. The 4th will likely be different from all 3. The 10th will probably exhibit properties we haven't imagined. There is no standard interstellar visitor. There's only diversity, strangeness, and constant surprise. And that diversity itself is evidence of something profound. The galaxy is not uniform. Stellar environments vary enormously. Different stars create different types of planetary systems. Different systems produce different types of debris when they're destroyed, and that debris, scattered throughout the galactic volume, represents a sampling of planetary formation outcomes across billions of years of cosmic history. We thought we could understand planetary system formation by studying our sun and its worlds. But that's like trying to understand human cultures by studying one small village. Yes, you'll learn something. Yes, there will be universal truths you can extract. But you'll miss the overwhelming majority of the diversity, the range of possibilities, the ways that different environments and histories produce radically different outcomes. Oumuamua taught us that interstellar objects can be completely unlike anything from our solar system. Dark, elongated, mysteriously accelerating, a cosmic mystery that we may never fully explain. 2I Borisov taught us that some interstellar visitors are recognizably comet-like, but with chemical signatures revealing their exotic origins, high carbon monoxide, fragile structure, evidence of formation in extremely cold environments around dim stars. 3I Atlas is teaching us that the surprises never stop. Metal vapor at impossible temperatures, extreme polarization signatures, carbon dioxide dominance, chemical and physical properties that don't match existing categories. And the next interstellar visitor, it will teach us something else, something we haven't thought to ask, something that violates a different set of expectations. Because that's the pattern. That's the lesson the galaxy keeps repeating. You don't understand. You can't understand. Your sample size is too small. Your experience is too limited. Your theories are based on one example, and one example is never enough. This should terrify us, because it means that when we eventually travel beyond our solar system, when we visit other stars and explore their planetary systems, we will encounter environments and conditions that we cannot predict from our limited experience. We will find worlds that operate according to principles we never imagined. We will discover forms of matter, types of chemistry, and perhaps even types of life that don't resemble anything in our neighbourhood. The 3 interstellar visitors are previews of that future. They are reminders that the universe is vaster, stranger, and more alien than our earthbound intuitions can grasp. Every time we think we understand the rules, reality sends us another message from the deep galaxy, another impossible object that breaks those rules and forces us to start over. But there's another possibility, one that the scientific community mostly dismisses, one that most astronomers find unlikely, but one that, given the strangeness of what we've observed, cannot be completely ruled out. What if some interstellar objects aren't natural at all? Avi Loeb, the Harvard astronomer who suggested Oumuamua might be an artificial light sail, has raised similar questions about 3I Atlas. Not because the comet looks artificial, it clearly doesn't. It exhibits all the characteristics of a natural object: outgassing, coma formation, dust tail, normal cometary behaviour. But Loeb's point isn't that 3I Atlas is obviously artificial. His point is that we cannot definitively prove it's natural, because we don't fully understand what we're looking at. The nickel vapour is anomalous. The polarization is unprecedented. The chemical composition is unusual. These could all be natural phenomena resulting from formation in an exotic stellar environment. But they could also be indicators of something else, something engineered. The possibility that an interstellar visitor could be a probe from another civilization is not science fiction. It's a logical conclusion based on known physics. If humanity developed interstellar travel capability, we would send probes to other star systems, robotic explorers designed to survey neighbouring systems and report back. It would be strange if an advanced civilization didn't do this. Exploration is a fundamental drive in intelligent species. Looking outward, seeking to understand the universe beyond our immediate neighbourhood, seems like a universal characteristic of consciousness. And if extraterrestrial civilizations have sent probes into the galaxy, then statistically, some of those probes should pass through our solar system. Just like natural interstellar objects, the galaxy is old. Civilizations could have arisen billions of years ago. Their probes might have been travelling for eons, their builders long extinct, but the machines they created still functioning, still executing their exploration protocols, still scanning every stellar system they encounter for signs of interest. Loeb's suggestion about Oumuamua was controversial precisely because it forced the astronomical community to confront this possibility, not as idle speculation, but as a hypothesis that must be considered and tested against the available data. And the conclusion most scientists reached was that while we cannot absolutely rule out artificial origin for Oumuamua, natural explanations are far more likely given Occam's razor and the lack of clear artificiality markers. The same logic applies to 3I Atlas. Yes, it's strange. Yes, it has anomalous properties. But strange and anomalous are not the same as artificial. The universe produces plenty of weird natural phenomena. Neutron stars, magnetaires, fast radio bursts, objects and events that seem impossible until we understand the physics that creates them. The responsible scientific position is to treat interstellar visitors as natural and lessened until clear evidence of artificiality emerges. Unusual chemistry is not such evidence. Unexpected physical properties are not such evidence. Even behaviours that seem to defy known physics are not sufficient evidence if natural explanations remain plausible. But here's where the situation gets philosophically interesting. If an extraterrestrial civilization wanted to send probes that would be ignored as natural objects, they could design them to look exactly like comets or asteroids, give them ice and rock surfaces, make them tumble chaotically, have them outgas normally, disguise the technology inside a shell of natural-appearing materials. Such camouflage would be trivial for an advanced civilization. This creates an unfalsifiable scenario. Any interstellar object could potentially be artificial, disguised to appear natural. And we would have no way to know unless we could examine it up close, perform detailed analysis, literally cut it open to see what's inside. From a distance, using spectroscopy and imaging, a cleverly disguised probe would be indistinguishable from a natural object. This is why most astronomers don't seriously entertain the artificial hypothesis for objects like 3I Atlas. Because if you allow for the possibility of perfect camouflage, then every interstellar visitor becomes a potential alien probe, and science devolves into paranoid speculation about what might be hiding inside apparently natural objects. Better to treat them as natural unless compelling evidence suggests otherwise. But the mere fact that we're having this conversation reveals something important about where humanity stands in 2025. We have now detected enough interstellar objects to know they're common. We have observed enough weirdness in those objects to know the galaxy produces phenomena we don't fully understand, and we are technologically capable enough that the idea of other civilizations sending probes no longer seems like fantasy. The possibility, however remote, that we might be sharing the galaxy with other intelligence is no longer confined to science fiction. It's a legitimate scientific question that demands serious analysis. And every interstellar visitor we detect is both an opportunity to learn more about natural galactic processes and a potential first contact scenario that requires careful consideration. For 3I Atlas, the consensus is clear. It's a comet. A strange comet with unusual properties, yes, but a comet nonetheless. Natural origin, no signs of technology, no artificial signals, just an ancient piece of ice and rock from another star system, passing through our neighbourhood on its eternal journey through the cosmos. But that consensus is based on current data, and we know from experience that new observations can completely overturn previous conclusions. Oumuamua was considered a comet until closer analysis revealed it had no visible coma or tail. 3I Atlas was initially unclear whether it was an asteroid or comet until observations confirmed cometary activity. The category assignments we make are provisional, subject to revision as better data arrives. So while 3I Atlas almost certainly is a natural object, we must remain open to surprises. Because if the first 3 interstellar visitors taught us anything, it's that these objects consistently defy our expectations. And assuming we fully understand what we're looking at is how we miss the truth. The real lesson of 3I Atlas isn't about whether it's natural or artificial. The lesson is about humility. We are a young species taking our first serious look at the debris field between stars. We're detecting objects from stellar environments we've never visited. We're observing materials formed under conditions we can only theorize about. We're trying to understand chemistry and physics operating in regimes we cannot replicate in laboratories. And we're doing all of this from a distance using instruments that, while remarkable, still have severe limitations. We cannot touch these objects. We cannot sample their ices. We cannot drill into their nuclei or examine their internal structure. We must infer everything from reflected or emitted photons captured across millions of miles of space. It's like trying to understand human civilization by examining a single grain of sand from a beach somewhere on Earth. Yes, that grain contains information. Its mineral composition tells you something about geology. Its size and shape reveal erosion processes. If you're very clever and very careful, you might even detect trace organic molecules or artificial contaminants that hint at biological activity. But you would miss everything important: the cities and cultures, the history and wars, the art and science, the complexity of human existence. Because one grain of sand, no matter how carefully analysed, cannot capture the full reality of the world it came from. That's our situation with interstellar visitors. We can measure their composition and trajectories. We can observe their outgassing and dust production. We can study their light curves and spectra. And from these measurements, we can infer some facts about their origins and properties. But we're missing the bigger picture. We're missing the stellar system they came from. We're missing the billions of years of history that shaped them. We're missing the context that would make their properties comprehensible instead of anomalous. We're looking at fragments of destroyed worlds, divorced from the environments that created them, and trying to reverse engineer those environments from limited data. Sometimes we'll succeed. Sometimes the chemical fingerprints will be clear enough to confidently identify formation conditions. But often we'll be left with mysteries. Anomalous properties that don't fit existing models, observations that challenge our understanding, reminders that the galaxy is far more complex than one stellar system can possibly teach us. 3I Atlas, with its vaporizing nickel and carbon dioxide dominance and extreme polarization, is one of those reminders. It doesn't fit neatly into our categories. It exhibits behaviours that shouldn't happen at the temperatures where we're observing them. It's telling us that somewhere in the galaxy, around some ancient star we'll likely never identify, conditions existed that could create this particular combination of properties. And the fact that we don't fully understand those conditions isn't a failure of science, it's a feature of reality. The universe is complicated. Stellar diversity is enormous. The range of possible planetary formation outcomes is staggering. And we, limited to observing one solar system in detail, are only beginning to glimpse that range. The 3 interstellar visitors are teachers, harsh teachers who grade by revealing how much we don't know, but teachers nonetheless. Each one expands our understanding of what's possible. Each one challenges our assumptions about how matter behaves in extreme environments. Each one forces us to update our models of galactic chemistry and dynamics. Oumuamua forced us to accept that highly elongated objects can exist naturally, and that acceleration without visible outgassing is possible under some circumstances. We still don't fully understand the mechanisms, but we know it happens. 2I Borisov showed us that high carbon monoxide comets can form around dim stars and survive ejection into interstellar space with their volatile ices intact. We learned that interstellar objects don't have to be completely alien. Some will resemble familiar solar system bodies. 3I Atlas is teaching us that metal vapor can appear at unexpected distances, and that polarization properties can be more diverse than we realized. We're still processing these lessons, trying to understand what they mean for our models of cometary composition and dust grain properties. And the 4th interstellar visitor will teach us something new. The 10th will teach us more. Each discovery will refine our understanding. Each anomaly will push the boundaries of what we consider possible. Each object will be a data point in a much larger picture of galactic diversity that we're only beginning to sketch. This is the scientific process at its most fundamental. Observation, surprise, analysis, updated models, repeat. The universe presents phenomena. We try to explain them. When our explanations fail, we don't give up. We gather more data. We revise our theories. We accept that reality is more complex than our current understanding. And gradually, painfully, we build better models. Not perfect models, better models. Closer approximations of the truth. Frameworks that explain more observations, predict more outcomes, fail less often when tested against new data. But we never reach complete understanding, because the universe is infinite in its complexity. There's always another layer of detail to discover, always another phenomenon that doesn't fit existing theories, always another surprise waiting to shatter our confident assumptions. The interstellar visitors are windows into that infinite complexity, brief glimpses of the galaxy's diversity, moments when the vast cosmic ocean that surrounds our tiny solar system allows a fragment of itself to pass close enough for us to observe. And each fragment tells a different story, shows us a different facet of reality, reveals another way that matter can organize itself under conditions we've never experienced. This should fill us with wonder and terror. Wonder at the richness of the universe, the endless variety of worlds and processes and outcomes. Terror at how little we know, how vast our ignorance, how precarious our understanding. We live in one solar system, one stellar environment, one chemical regime, one gravitational well. Our entire scientific worldview is built from observations of this one example. And now, finally, we're starting to receive messages from beyond, objects from other examples, visitors from different regimes, and they're showing us, one anomalous property at a time, how much we have left to learn. 3I Atlas will soon be gone. Already it's moving away from the Sun, heading back toward interstellar space on its hyperbolic trajectory. Within a few years, it will cross the outer edge of the heliosphere, leaving our solar system's sphere of influence and returning to the galactic environment. Within decades, it will be too far and too faint for even our best telescopes to detect. Within centuries, it will have travelled light years from us, on its way to potential encounters with other stellar systems millions or billions of years from now. We will never see it again. This one passage was our only opportunity, and while we've learned much, we've also accumulated more questions. The nickel vapour remains unexplained. The polarization properties are unprecedented. The carbon dioxide dominance suggests formation conditions we can only speculate about. Every answer has generated new mysteries, but that's how knowledge advances, not through complete understanding, but through progressively better questions. We started by asking, what is that moving object? We progressed to, is it from outside the solar system? We moved on to, what is it made of and where did it come from? And now we're asking, what processes can create these specific properties, and what does that tell us about stellar environments we've never observed? Each question is more sophisticated than the last. Each requires deeper understanding to properly frame, and each answer, partial and uncertain as it may be, moves us one step closer to comprehending the galaxy we inhabit. The comparison with Oumuamua and Borisov amplifies these lessons. 3 objects, 3 wildly different sets of properties, 3 unique windows into galactic diversity. Together, they paint a picture of a galaxy far more complex, far more varied, and far more alien than our solar system sample could ever suggest. And this is just the beginning. 3 confirmed interstellar detections in 8 years, dozens or hundreds potentially waiting to be discovered in the next decade. Each one different, each one strange, each one carrying secrets from regions of space we'll never visit directly. We are living through the dawn of interstellar object astronomy, a new field of study born from the realization that the space between stars is not empty, but filled with wandering messengers from distant systems. We're learning to read those messages, to extract information from chemical signatures and physical properties, to reverse engineer stellar environments from fragmentary evidence. But we're beginners at this, stumbling through our first efforts, making mistakes, missing details, forming conclusions that later observations will overturn. That's normal. That's how science works when confronting genuinely new phenomena. The danger is premature certainty. The temptation to declare we understand these objects when we've barely begun to study them. The hubris of thinking that theories built from 3 examples can accurately predict the properties of the 4th. We must resist that temptation. We must remain humble, open to surprise, willing to abandon cherished models when data contradicts them. This is harder than it sounds. Human psychology craves certainty. We want to believe we understand. We want our theories to be correct. We want the universe to make sense according to principles we've already discovered. But the universe doesn't care what we want. It operates according to its own rules, and those rules, when they finally become clear, are always stranger and more beautiful than our preliminary guesses. 3i Atlas is a reminder of this truth. Every anomalous property is the universe saying your current understanding is incomplete. Every violation of expectations is an invitation to think more deeply, look more carefully, and question assumptions you didn't even know you were making. The nickel vapour, the carbon dioxide dominance, the polarization anomalies. These aren't errors in measurement or flaws in the data, they're signals, messages from the deep galaxy. Letters in a cosmic alphabet we're only beginning to learn to read. And the message says, you don't know what you don't know. The galaxy is vast. Stellar environments are diverse. Planetary formation follows pathways you haven't imagined. And the debris from billions of years of cosmic violence is stranger than your theories predict. This message should change how we think about our place in the universe. We are not the centre. We are not the template. We are one outcome among countless possibilities, one chemical regime among millions, one planetary system architecture among infinite variations. And when we look beyond our immediate neighbourhood, when we observe the galaxy at large, we will encounter phenomena and objects and perhaps even life that doesn't resemble anything from our familiar solar system. We will be surprised, constantly, perpetually, because diversity is the fundamental nature of cosmic evolution. The 3 interstellar visitors have shown us this truth: Oumuamua, Borisov, and Atlas. 3 messengers from the deep galaxy. 3 reminders that we are cosmic provincials, inhabitants of a tiny oasis in an ocean we barely comprehend. But here's the final thought, the most important realization, the conclusion that should guide our future exploration of the cosmos. These objects are not anomalies. They are not exceptions. They are the norm. We are the anomaly. Our solar system, with its particular arrangement of planets and composition of materials, is the exceptional case, one outcome in a galaxy-spanning probability distribution. And that distribution includes configurations far stranger than anything we've observed in our neighbourhood. So when the next interstellar visitor arrives, when 4i appears in our detection systems and astronomers scramble to observe it before it departs, we should expect the unexpected. We should anticipate properties that don't match existing categories. We should prepare for chemistry that violates current models. Because that's what the galaxy does. It produces diversity. Endless, inexhaustible diversity. And we, limited to our one solar system, one stellar environment, one chemical regime, are only just beginning to appreciate how diverse the cosmos truly is. 3i Atlas is sailing away from us now, moving at over 200,000 kilometers per hour, bleeding its impossible nickel vapor into the void, carrying its ancient ices formed billions of years ago around a star we'll never identify. Returning to the dark ocean between suns where it has spent most of its existence. It came to us by chance, a random intersection of trajectories in the vast emptiness of space. We detected it, we studied it, we learned from it, and now it's leaving. But it's not gone, not really. The data remains, the spectra and images and measurements, the questions it raised and the models it challenged, the reminder that the universe is stranger, vaster, and more alien than we dare imagine. And somewhere out there, right now, another object is approaching, another fragment of a destroyed world, another messenger from the deep galaxy. Maybe we'll detect it, maybe it will pass unseen, but it's coming, and behind it, thousands more. An endless stream of cosmic debris flowing through our neighbourhood, carrying secrets from stellar environments we'll never visit. This is our future. Learning to read the messages written in wandering fragments of alien worlds, decoding the chemical signatures of distant stellar systems, slowly, painfully, building an understanding of the galaxy that extends beyond our tiny solar system perspective. It will take centuries, millennia, perhaps longer. But every interstellar visitor brings us one step closer. Every anomalous property is a clue. Every violation of expectations is a lesson. Oumuamua, Borisov, Atlas. 3 names, 3 objects, 3 glimpses of cosmic diversity. And the lesson they teach to get at us is humility. We don't know. We can't know. Not from here. Not from this limited vantage point. But we can observe. We can measure. We can question and learn and slowly expand our understanding. The galaxy is waiting, patient, ancient, filled with wonders we haven't imagined and horrors we can't comprehend, and it's sending us messengers, one by one, fragment by fragment, teaching us, in the only way it can, that reality is always stranger than our theories predict. 3i Atlas is one such messenger, and its message is clear. You're not alone in the galaxy, but what surrounds you is not what you think. The space between stars is not empty. It's filled with the remnants of worlds that died before your sun was born, and each remnant carries a story you need to hear. But this story is far from over, because while 3i Atlas sailed past the Sun and began its journey back toward interstellar space, something happened that transformed a scientific mystery into a political scandal. And what that scandal revealed about the comet makes everything we thought we understood about this visitor seem incomplete. On October 2nd and 3rd, 2025, as 3i Atlas came within 29 million kilometres of Mars, 7 different spacecraft turned their instruments toward the interstellar visitor. The European Space Agency's ExoMars Trace Gas Orbiter captured colour images. China's Tianwen-1 Mars Orbiter recorded the comet's passage across the Martian sky. NASA's Perseverance rover, sitting on the surface of Mars, pointed its navigation camera upward and photographed what appeared to be an elongated streak against the darkness of space. But the most important observations came from NASA's Mars Reconnaissance Orbiter. The HiRISE camera, the highest resolution imaging system ever sent to Mars, captured detailed side-view images of 3i Atlas with a spatial resolution of 30 kilometers per pixel. This resolution is 3 times better than the Hubble Space Telescope images taken in July. For the first time, we would have high-resolution views of the comet's anti-tail from a perspective angle that could reveal its true structure and behaviour, and then NASA locked those images away for 43 days and counting. The images were taken on October 3rd. The government shutdown began on October 7th, just 4 days later. And suddenly, some of the most scientifically valuable images of an interstellar visitor ever captured became hostages to bureaucratic paralysis. NASA officials stated that agency policy prohibits the release of data during a government shutdown. The images sat in digital archives, unseen, while the comet continued moving away from the Sun, getting fainter with each passing day. The astronomical community erupted in frustration. These images are time-sensitive. Scientists need them to plan follow-up observations. Every day of delay means less light from the comet, fewer photons reaching telescopes, narrower windows for coordinated studies across multiple instruments. You cannot pause cosmic events and restart them when bureaucracy permits. The universe operates on its own schedule. Avi Loeb, the Harvard astronomer who's been coordinating international observations of 3i Atlas, called the situation unconscionable. Scientific knowledge should not be second in priority to bureaucracy, he wrote. The public interest in the mysteries of 3i Atlas is unprecedented. He described how even calling to order a replacement dishwasher became a conversation about the comet when the customer service representative recognized his voice from television interviews. Representative Anna Paulina Luna, a congresswoman from Florida, took the unusual step of writing an official letter to NASA's interim administrator, demanding the release of the images. This information is of great importance to advancing our understanding of interstellar visitors and their interaction with our solar system, she wrote. When that letter produced no immediate results, she went public. As soon as the government reopens, they'll be releasing images and data, she tweeted. Unfortunately, due to bureaucratic reasons, they cannot until then. Think about what this means. We detected only our 3rd interstellar visitor in human history. Multiple spacecraft captured unprecedented observations of it during a close planetary approach. The highest resolution images ever obtained of such an object are sitting in NASA's databases, and they're being withheld not for scientific reasons, not because they need additional analysis, but because of a political dispute about government funding that has nothing to do with astronomy. The shutdown has since ended, but as of mid-November 2025, the HiRISE images remain unreleased. The bureaucratic machinery turns slowly. The scientific community waits. And 3i Atlas continues moving away from the Sun, getting dimmer, the opportunity to correlate the HiRISE observations with current telescope data slowly slipping away. But while we wait for NASA to unlock its treasure trove of Mars orbiter data, the Chinese have been less constrained by bureaucracy. The China National Space Administration released images from the Tianwen-1 orbiter's high-resolution imaging camera captured during the same October 3rd flyby. The resolution is inferior to HiRISE, The 38.7cm primary mirror smaller than HiRISE's 50cm aperture. But the images reveal crucial information nonetheless. The Chinese images show 3I Atlas as a fuzzy ball of light surrounded by a coma several thousand kilometers in diameter. The nucleus itself is too small to resolve directly, appearing as a bright concentrated glow at the center of the diffuse cloud. The Chinese team created an animation from a series of 30-second exposures, tracking the comet's motion across the Martian sky, a cosmic wanderer drifting past the red planet on its long journey through the void. The fact that we're relying on Chinese data while NASA's superior observations remain locked away is both ironic and frustrating. International scientific cooperation should mean that the best available data gets shared rapidly to advance human knowledge. Instead, we have a situation where political considerations delay the release of images that could answer fundamental questions about the nature of interstellar objects. What questions could those HiRISE images answer? The most critical one involves the comet's size. The brightest pixel in the HiRISE image would provide the tightest constraint yet on the diameter of 3I Atlas's nucleus. Current estimates range from 440 meters to 5.6 kilometers, an uncertainty factor of more than 10. That's the difference between a small mountain and a decent-sized city. The HiRISE data could narrow that range dramatically, potentially even resolving the nucleus directly if it's on the larger end of current estimates. The images would also reveal the detailed structure of the comet's jets and anti-tail. Remember, the Hubble observations in July showed an anomalous jet pointing toward the Sun, something that shouldn't exist on a normal comet, because solar radiation pressure pushes dust away from the Sun, not toward it. The HiRISE images provide a side-view perspective of these jets from a different angle than any previous observation. This geometric variety is crucial for reconstructing the three-dimensional structure of the gas and dust flowing from the comet. But we don't have access to those images, so instead we must work with what is available, and what's available is increasingly strange. November 11th, 2025, the comet re-emerged into the morning sky after spending weeks behind the Sun from Earth's perspective. Astronomers at the Nordic Optical Telescope pointed their instruments toward the returning visitor and captured new high-resolution images. And what those images revealed sent shockwaves through the astronomical community monitoring this object. The anti-tail is still there, still pointing toward the Sun, still defying the basic physics of how cometary tails should behave. In the Nordic Optical Telescope images, you can see it clearly. A jet of material extending from the nucleus directly toward the Sun's position. The projected anti-solar direction is marked on the processed images, showing that the jet is indeed sunward, not an optical illusion from perspective effects. This feature has persisted for at least 4 months now, from July through November, remaining visible even as the comet moved past perihelion and began its outbound journey. No known physical process can explain this. Solar radiation pressure pushes dust away from the Sun. The solar wind, a stream of charged particles constantly flowing outward from our star, also pushes material away. Every force we understand acts to create tails that point away from the Sun, following the direction of radiation and particle flow. Yet 3I Atlas maintains a prominent feature that does exactly the opposite. David Jewett, one of the astronomers who confirmed the comet's activity in early July, has suggested that the anti-tail might be composed of unusually large dust particles, around 100 micrometers in radius. These giant particles are 1,000,000 times more massive than typical cometary dust. Because the ratio of surface area to mass decreases as particles get larger, these giant grains wouldn't be pushed away from the Sun as effectively as smaller dust. They might hover near the nucleus, creating a structure that appears to point sunward from certain viewing angles. But this explanation has problems. To maintain a jet extending hundreds of thousands of kilometers toward the Sun, continuously for months, requires enormous amounts of these giant particles being released at precise angles. And the jet shows up in multiple images from different viewing geometries, suggesting it's not just a perspective effect. Another possibility, as Jewett and colleagues have noted, involves ice fragments rather than refractory dust. If chunks of ice are ejected from the nucleus and begin scattering sunlight before they sublimate completely into gas, they might create a sunward feature. But ice fragments don't last long near the sun. They evaporate within hours or days at most. To maintain the anti-tail for months would require a continuous supply of fresh ice being ejected in exactly the right direction. Then there's the more speculative explanation. What if the anti-tail isn't caused by passive dust or ice at all? What if it's a collimated jet of material moving at high velocity, fast enough to penetrate through the solar wind and extend sunward, before being deflected? Natural outgassing from comets produces speeds of a few hundred meters per second at most, but a jet moving at several kilometers per second could potentially maintain directionality even against the solar wind. Such high-velocity jets are not normal for comets. But then again, nothing about 3I Atlas has been normal from the beginning. The November images revealed something else equally puzzling. Multiple jets extending in different directions. November 8th images captured by Michael Yeager, Gerald Riemann, and Enrico Prosperi showed a complex tail structure with 4 to 5 distinct jets, or tails, fanning out from the nucleus in multiple directions. This multi-tail structure resembles only one other comet in our records, C2016 R2, an unusual long-period comet extremely rich in carbon monoxide and nitrogen, but poor in dust. The comparison to C2016 R2 is both enlightening and disturbing. That comet's unusual chemistry suggested formation in an exceptionally cold environment, where carbon monoxide and nitrogen could condense alongside water ice. Its multiple tails resulted from its chemical composition, creating different outgassing rates in different directions, as various ices sublimated at different temperatures. If 3I Atlas is exhibiting similar multi-tail behaviour, it reinforces the conclusion that its composition is radically different from typical solar system comets. The carbon dioxide dominance that James Webb detected, combined with the nickel vapour observed by ground telescopes, and now this multi-directional jet structure, all point to formation conditions unlike anything in our neighbourhood. But here's where the mystery deepens even further. Those dramatic multi-directional jets, extending millions of kilometres from the nucleus, appeared in early November. Yet by November 11th, new observations showed something impossible. The comet still exists as a single body. Let me explain why this is a problem. When astronomers analysed the size and brightness of the jets visible in the November 8th and 9th images, they could calculate the amount of material being expelled. The sunward jet extends about 1 billion kilometres. The jets in the opposite direction reach roughly 3 million kilometres. For a natural comet with typical outgassing velocities around 400 meters per second, these jets must have been continuously active for 1 to 3 months to reach those distances. The mass flux required to create and maintain jets of that scale is staggering. Avi Loeb calculated that the jets would need to be ejecting approximately 5 billion tons of material per month. Most of that material is probably carbon dioxide based on the James Webb spectroscopic observations. To sublimate that much CO2 requires an enormous amount of energy, about 3 times 10 to the power of 18 joules, over the course of a month near perihelion. Where does that energy come from? The Sun. At the comet's perihelion distance, solar radiation provides about 700 joules per square metre per second. To capture enough solar energy to sublimate 5 billion tons of carbon dioxide requires an absorbing surface area of at least 1,600 square kilometres. That's the surface area of a sphere with a diameter of 23 kilometres. But here's the problem. Hubble observations constrain the maximum diameter of 3I Atlas to 5.6 kilometres. Even if the true size is at the upper end of that range, the surface area is nowhere near large enough to absorb the energy needed to produce the observed jets. The numbers are off by a factor of at least 15, and potentially much more if the nucleus is on the smaller end of current size estimates. For a natural comet, there's only one solution to this energy budget problem. The nucleus must fragment into multiple pieces, increasing the total surface area exposed to sunlight. When 2I Borisov, the previous interstellar visitor, passed through perihelion, it broke apart into at least 2 major fragments plus a debris field of smaller pieces. This fragmentation allowed more surface area to sublimate, producing the observed activity. Based on the energy requirements, Loeb calculated that 3I Atlas should have broken into at least 16 separate fragments to account for the observed outgassing. The tidal stresses near perihelion, combined with the thermal stress of rapid heating, should have torn the nucleus apart if it's a typical weakly bound cometary rubble pile. But the November 11th images from the Nordic Optical Telescope show a single bright nucleus. No evidence of fragmentation, no trail of debris, just one concentrated source of light surrounded by its coma and jets. The comet made it through perihelion intact, holding together despite forces that should have destroyed it. This structural integrity is deeply puzzling. Normal cometary nuclei are fragile. They're often described as dirty snowballs, but that's actually too generous. They're more like loosely packed collections of ice and rock, held together by barely more than their own weak gravity and the mechanical strength of frozen volatiles. When you subject such an object to the thermal and tidal stresses of a close solar passage, while simultaneously losing huge amounts of mass through outgassing, fragmentation is almost inevitable. Yet 3I Atlas survived. Either its nucleus is much larger than observations suggest, providing enough gravitational self-attraction to resist fragmentation, or its internal structure is significantly stronger than typical comets. Neither option fits comfortably with the other observations we have. If the nucleus is larger, perhaps 20 or 30 kilometers across instead of the 5.6 kilometer maximum that Hubble suggested, then the energy budget problem goes away. A larger surface area can absorb enough solar radiation to drive the observed outgassing. But then we face a different problem. Why do all the imaging observations, from Hubble to the ground-based telescopes to the Mars orbiters, consistently indicate a much smaller size? Is the nucleus unusually dark, reflecting so little light that it appears smaller than it actually is? If the nucleus is the size that observations suggest but has unusual structural strength, what does that imply about its composition or formation? Comets from our solar system acquire their fragile rubble pile structure during formation in the protoplanetary disk. Small particles stick together through low-velocity collisions, building up larger bodies without compacting into solid structures. But what if comets in other stellar systems form differently? What if the star that birthed 3I Atlas had a protoplanetary disk with different densities or temperatures that allowed for more compacted nucleus formation? Or what if the billions of years of radiation processing in interstellar space altered the comet's structure? Cosmic rays and ultraviolet photons can drive chemical reactions in surface layers, potentially creating a hardened radiation-processed crust. We know from the observations that 3I Atlas has a reddish colour caused by tholins, complex organic molecules created by radiation. Could that same radiation have welded the surface layers into a more cohesive structure, capable of resisting fragmentation? These are not idle speculations. They are attempts to reconcile observations that don't fit together. The comet exhibits extreme activity suggesting a large surface area or unusual volatility, yet it maintains structural integrity suggesting either great size or unusual strength. It produces jets that point toward the sun using mechanisms that remain unclear, and it does all this while following a trajectory that itself raises questions. This brings us to Avi Loeb's list of anomalies. As observations accumulated throughout July, August, September, October, and now November, Loeb has been documenting properties of 3I Atlas that deviate from expectations. By mid-November, his list had grown to 12 distinct anomalies, 12 ways in which this comet doesn't behave like natural objects should. Let's go through them, because when you see all 12 together, the cumulative weight of weirdness becomes almost overwhelming. Anomaly 1. The trajectory alignment. 3I Atlas is moving on a retrograde orbit tilted 175 degrees relative to the ecliptic plane. This means it's moving in the opposite direction from the planets and most solar system objects. That's not surprising for an interstellar interloper. What is surprising is how precisely aligned the trajectory is with the ecliptic plane. The inclination is only 5 degrees off. The probability of this happening by chance is approximately 0.2%. Most interstellar objects should have random orientations because they're coming from random directions in the galaxy. But 3I Atlas's orbit is suspiciously well aligned with the plane where all the planets orbit. Anomaly 2. The persistent sunward jet. We've already discussed this at length. The anti-tail pointing toward the sun for at least 4 months is unexplained by conventional cometary physics. Every proposal for how this feature might arise requires special pleading or exotic conditions. Anomaly 3. The mass and velocity. 3I Atlas is roughly 1 million times more massive than Oumuamua and 1,000 times more massive than 2I Borisov. Yet, it's moving faster than both previous interstellar visitors. The probability of detecting an object this massive moving this fast is less than 0.1% based on statistical models of interstellar object populations. We should be seeing more small, fast objects or large, slow objects. Instead, we found a large, fast object on our third detection. That's statistically unlikely. Anomaly 4. The arrival timing. The comet's trajectory brought it within tens of millions of kilometers of Mars, Venus, and Jupiter. It was unobservable from Earth during perihelion because it passed behind the Sun from our perspective. This specific geometry has a probability of about 0.05%. While any trajectory has some low probability, this particular one seems almost designed to provide close approaches to multiple planets, while avoiding easy observation from Earth's surface during the most active phase. Anomaly 5. The unusual composition. The carbon dioxide dominance and nickel vapor we've already covered, but it's worth emphasizing again how unusual this combination is. Very few objects show nickel emission, and those that do typically require much higher temperatures than exist at 3I Atlas's distance from the Sun during the observations. Anomaly 6. The extreme negative polarization. The polarimetric observations showing that deep, narrow negative polarization branch don't match any known comets or asteroids. The measurements place 3I Atlas in a category by itself, not fitting into high polarization comets, low polarization comets, or the rare category occupied by Hale-Bopp and 2I Borisov. Anomaly 7. The colour evolution. The comet's reddish colour has changed over time. Observations in July showed one shade. By August, it had reddened further as activity increased and fresh material sublimated from below the surface crust. This evolution is faster than typical for solar system comets, suggesting that the surface layers are less stable or more chemically active. Anomaly 8. The rotation period. Analysis of brightness variations in July and August indicated a rotation period of 16.16 hours, plus or minus 0.01 hours. This precision is itself unusual, but more importantly, the rotation period doesn't seem to be changing despite the enormous mass loss from outgassing. For a normal comet, losing billions of tons of material through asymmetric jets would alter the rotation rate through conservation of angular momentum. Yet 3I Atlas's rotation appears stable. Anomaly 9. The brightness outburst. During the approach to perihelion in late October, the comet suddenly brightened much faster than predictions suggested. Space-based observatories detected it reaching magnitude 7 to 8, far brighter than the magnitude 11 to 12 that models predicted. This outburst suggests that something changed in the comet's activity level, possibly a large pocket of volatile ices becoming exposed or a fragmentation event. But if fragmentation occurred, we should see multiple nuclei. We don't. Anomaly 10. The hydrogen cyanide production. Observations with the James Clerk Maxwell Telescope in early September detected hydrogen cyanide outgassing at a rate of 1.5 times 10 to the 25th molecules per second. A week later, the rate had tripled to 4.5 times 10 to the 25th molecules per second. This rapid increase suggests that activity was ramping up faster than models predicted, possibly due to fresh material being exposed as surface layers sublimated away. Anomaly 11. The multi-directional jet structure. The 4 to 5 distinct jets visible in November, images all appear to maintain their directionality despite the comet's rotation. For a tumbling nucleus, you'd expect jets to sweep across the sky as different faces rotate into sunlight. But the jet orientations in the images suggest they're more stable than rotation alone would allow. Anomaly 12. The missing tail paradox. This is perhaps the most recent and most puzzling anomaly. Based on the amount of material the comet must have lost during perihelion, there should be a massive dust and gas tail extending millions of kilometers away from the Sun. November 5th, images show no such tail. The comet appears to have jets and the anomalous anti-tail, but the normal cometary tail that should dominate the appearance is conspicuously absent. Let me emphasize that last point because it's crucial. When a comet loses 13% or more of its mass during perihelion passage, as Loeb calculated for 3I Atlas, that material doesn't just disappear. It forms a coma of gas and dust that gets pushed away from the Sun by radiation pressure and solar wind. Every comet we've ever observed near the Sun develops a prominent tail in the anti-solar direction. That's what makes comets visually spectacular from Earth. But 3I Atlas, which should have one of the most prominent tails based on its mass loss, instead shows only the mysterious jets and anti-tail structure. Where did all the ejected material go? Why isn't there a normal cometary tail pointing away from the Sun? One possibility is that most of the ejected material is in the form of gas rather than dust. Gas doesn't scatter sunlight as effectively as dust particles, so a gas-dominated coma might be much less visible in optical images. But spectroscopic observations should easily detect strong emission lines from the gas. And while we do see carbon dioxide, hydrogen cyanide and other species, the quantities don't seem sufficient to account for all the missing mass. Another possibility is that the dust particles are unusually large or have unusual optical properties that make them less visible than a typical cometary dust. Remember the suggestion about 100 micrometer radius giant particles to explain the anti-tail? If most of the dust is in such large grains, they wouldn't scatter light as efficiently, making the tail dimmer than expected. But producing such a large fraction of giant dust grains is itself unusual and requires explanation. Or perhaps the material is being ejected at high velocity and escaping the comet's vicinity entirely before it can accumulate into a visible tail. But that requires ejection velocities much higher than typical cometary outgassing produces, which brings us back to the question of what mechanism could accelerate material to such speeds. Each anomaly, considered individually, might have a natural explanation requiring only mildly unusual conditions. But 12 anomalies, all present in the same object, stretches coincidence to the breaking point. This is not a slightly unusual comet. This is an object that violates expectations systematically across multiple independent observables. And this is why Avi Loeb, despite knowing how controversial the suggestion is, cannot completely rule out the possibility of artificial origin. Not because he believes 3I Atlas is definitely artificial, but because when an object exhibits this many anomalies, the responsible scientific approach is to consider all possibilities, including unlikely ones, and test them against the data. The artificial hypothesis faces severe problems. The comet exhibits active outgassing, something that suggests icy volatiles sublimating from a natural nucleus. It has a visible coma and jets consistent with cometary processes. No spacecraft we can build would disguise itself so thoroughly as a comet, while simultaneously maintaining all these unusual properties. But here's the uncomfortable truth. if an advanced civilization wanted to send a probe that would be overlooked as a natural object, disguising it as a comet would be an effective strategy. Coat it in ice and rock. Let it outgas naturally as it approaches stars. Make sure it tumbles and exhibits properties consistent with cometary behaviour. Such a probe would pass through stellar systems appearing to be nothing more than an interstellar comet, ignored by astronomers as just another piece of galactic debris. We cannot prove that 3I Atlas is artificial, but we also cannot definitively prove that it's natural, because natural implies we understand the processes that created it, and right now, we don't. We can propose mechanisms for each anomaly, but those mechanisms remain speculative, untested, and in many cases physically unclear. The high-rise images sitting in NASA's archives might help resolve some of these questions. They might show details of the nuclear structure that clarify whether fragmentation occurred. They might reveal the three-dimensional geometry of the jets in ways that constrain the physics of their formation. They might provide the missing puzzle pieces that make the comet's behaviour comprehensible, or they might add new mysteries, because that's been the pattern with 3I Atlas. Every new observation has raised as many questions as it's answered. Every dataset has revealed properties we didn't expect. Right now, in mid-November 2025, 3I Atlas is visible in the morning sky for observers with telescopes. It's located in the constellation Virgo, rising before sunrise, magnitude 10 to 12, too faint for naked eye visibility but well within reach of modest amateur equipment. The comet will continue to be observable through December as it climbs higher in the pre-dawn sky, though it will fade rapidly as it moves away from the sun. This is our last opportunity. Within weeks, it will become too faint for anything except the largest professional telescopes. By early 2026, it will have moved beyond practical observation range for most instruments. The comet will continue its journey back toward interstellar space, passing Jupiter at a distance of 54 million kilometers in March 2026, then crossing the outer solar system boundary and returning to the galactic environment. We will never see it again. Every observation we make in these coming weeks is irreplaceable. Every spectrum, every image, every measurement adds to our permanent record of this visitor. When 3I Atlas disappears into the cosmic void, it will carry away its secrets unless we extract them now. The astronomical community is mobilizing every available resource. The James Webb Space Telescope is scheduled to observe the comet again in December, after perihelion, looking for changes in its spectrum that might reveal how the close solar passage affected its composition. Hubble is conducting ultraviolet spectroscopy to determine the sulfur-to-oxygen ratio in the gas emissions, which will provide clues about the comet's formation environment. Ground-based observatories around the world are tracking its position, measuring its brightness, analysing its spectra, looking for any changes in its behaviour as it moves away from the sun. Amateur astronomers with modest equipment are contributing observations that, when combined with professional data, provide time-resolved coverage that no single observatory could achieve alone. The Virtual Telescope project in Italy has been hosting live streams, showing real-time views of the comet as it evolves. These streams have attracted thousands of viewers, people around the world watching an interstellar visitor make its way through our cosmic neighbourhood. There's something profound about that collective experience. This object came from another star system. It's been travelling for billions of years, and for a few months in 2025, it passed close enough for us to see it, to study it, to wonder about its origins and nature. But the sense of wonder is mixed with frustration. The high-rise images remain locked away. The government shutdown has ended, but the bureaucratic processes for data release move slowly, scientists wait, time passes, the comet fades. There's a broader lesson here about how we handle rare cosmic opportunities. Interstellar visitors don't arrive on convenient schedules. We detected Oumuamua after it had already passed perihelion and was heading outbound. We had only a few weeks to study it before it became too faint. We missed crucial details because our detection came too late, and our response wasn't fast enough. With 2I Borisov, we did better. Amateur astronomer Gennady Borisov discovered it while it was still approaching perihelion, giving us months to prepare observations. We learned more from Borisov than from Oumuamua because we had time to coordinate campaigns across multiple telescopes and instruments. 3I Atlas falls somewhere in between. We detected it roughly 4 months before perihelion, providing time for some preparatory observations but not enough to fully optimize the campaign. And then the political shutdown locked away some of the most valuable data at exactly the wrong moment. This cannot happen again. When the 4th interstellar visitor arrives, and it will arrive, we need systems in place for rapid data sharing regardless of political circumstances. We need automated pipelines that can release calibrated data within days rather than months. We need international agreements that prioritize scientific value over bureaucratic protocols for time-sensitive targets. Because these objects are rare. The Vera C. Rubin Observatory, which will begin full operations in the coming years, should dramatically increase our detection rate. Optimistic estimates suggest dozens to hundreds of interstellar visitors might be detected annually once Rubin is operational. But even with increased detection, each object remains a unique scientific opportunity. We'll never study this particular comet again. The information we fail to gather now is lost forever. And there's a deeper issue lurking beneath the technical frustrations, the 12 anomalies, the unexplained behaviours, the systematic violations of expectations. What do they mean? The conservative interpretation is that 3I Atlas is simply a very unusual natural comet, formed under exotic conditions in another stellar system. Every anomaly has a natural explanation we just haven't discovered yet because our models are built from observations of our solar system and don't adequately capture the full range of possibilities in galactic comet populations. This interpretation is probably correct. Most astronomers believe it's correct. The burden of proof for an extraordinary claim like artificial origin is appropriately high. We should assume natural processes unless the evidence overwhelmingly points to artificial ones. And despite all the anomalies, we don't have that overwhelming evidence. But here's what keeps scientists awake at night. What if the conservative interpretation is wrong? What if some interstellar objects are artificial? What if some fraction of the galactic debris field consists of probes sent by other civilizations? The implications would be profound. It would mean we're not alone. It would mean the galaxy has a history of technological intelligence spanning billions of years. It would mean that our solar system, far from being isolated, is being surveyed by remnants of civilizations we may never encounter directly. And we might never know. Because distinguishing a sufficiently well-designed probe from a natural object might be impossible at the distances and resolutions where we observe these visitors. Unless a probe wants to be recognized, unless it does something overtly artificial, it could pass through our system appearing to be just another interstellar comet. This is why the high-rise images matter so much. This is why every observation matters. We're not just cataloguing the properties of space rocks. We're searching for truth about our place in the cosmos. Are we alone? Is the galaxy filled with dead worlds and inert debris, or is there, hidden among the natural objects, evidence of intelligence? 3I Atlas probably won't answer that question definitively. It almost certainly is a natural comet with unusual properties, explainable by exotic formation conditions, but the probability isn't zero that it's something else. And as long as that probability exists, we have a responsibility to look carefully, measure precisely, and remain open to surprises. The coming weeks will be crucial. The observations being gathered right now will form the basis for scientific papers analysing this object for years to come. Researchers will pore over the data, searching for patterns, testing hypotheses, building models to explain what we've seen. Some mysteries will be solved. The nickel vapor might be explained by a particular mineral composition heated to just the right temperature. The anti-tail might turn out to result from a geometrically specific combination of large dust grains and viewing angle. The structural integrity might indicate a nucleus size at the upper end of current estimates. But some mysteries will remain. We'll probably never know with certainty which star system birthed this comet. We'll probably never pin down its exact age beyond the rough 3 to 11 billion year estimate. We'll probably never visit it with a spacecraft to analyse it directly. The detailed composition of its interior will remain unknown. The full story of its billions of years wandering through the galaxy will never be told, and that uncertainty is something we'll have to accept, because this is the nature of studying interstellar visitors. They're messengers from beyond our reach, carrying information we can only partially decode. They arrive unexpectedly, stay briefly, and leave permanently. We gather what data we can and make the best inferences possible from limited observations. But limited doesn't mean useless. Even with all the unknowns, we've learned enormous amounts from 3i, Atlas. We've learned that interstellar comets can have chemical compositions radically different from solar system comets. We've learned that massive interstellar objects can maintain structural integrity under conditions that would destroy typical comets. We've learned that cometary behaviour is more diverse and strange than our models anticipated. We've also learned humility. Every confident prediction about what this comet would do has been undermined by observations showing it doing something different. Will it brighten at this rate? No, it brightens faster. Will it fragment at perihelion? No, it survives intact. Will it have a normal tail after perihelion? No, the tail is mysteriously absent. This pattern of surprise should teach us caution in making confident predictions about future interstellar visitors. Each one will be different. Each one will exhibit properties we haven't seen before. The range of possible chemistries, structures, and behaviours in galactic debris populations is larger than we imagined. And that's actually exciting, because it means the universe is richer, stranger, and more complex than our theories suggested. Every violation of expectations is an invitation to expand those theories, to build better models, to deepen our understanding of how matter behaves under conditions we can't reproduce in laboratories or simulate in our solar system. 3i Atlas is teaching us that lesson one anomaly at a time. 12 so far. Perhaps more to come as analysis continues. Each one is a gift, a clue pointing toward deeper truths about galactic processes we're only beginning to glimpse. The comet doesn't care that it's teaching us. It's not conscious of its role as cosmic messenger. It's just a chunk of ice and rock, following its trajectory through space according to the same laws of physics that govern everything else. But from our perspective, trapped in one solar system, dependent on rare visitors to bring us information about the broader galaxy, each interstellar object is precious. And this one, with its nickel vapor and carbon dioxide dominance and anti-tail and structural strength and 12 documented anomalies, is teaching us more than we could have hoped. But the lessons aren't over. Because right now, as 3i Atlas moves through the dawn sky, it continues to change, continues to reveal new facets of its nature. The observations coming in these final weeks before it fades from view will add new chapters to its story. The high-rise images, when they're finally released, might rewrite sections we thought we understood. This is science at its most fundamental. Observation, mystery, analysis, revised understanding, and perpetual awareness that nature is under no obligation to conform to our expectations. The universe operates according to its own logic, following principles that might take centuries to fully comprehend. 3i Atlas came to us by chance, a random intersection of trajectories in the vast emptiness of space. We didn't summon it. We didn't plan its arrival. We simply looked up and found it passing by, a cosmic wanderer allowing us a brief glimpse of galactic conditions far beyond our reach. What we do with that opportunity defines us as a scientific civilization. Do we carefully observe and analyse, extracting every bit of information possible? Do we share data freely and rapidly to maximise scientific return? Do we remain open to surprises while maintaining rigorous skepticism? Do we let political considerations override scientific imperatives? The way we've handled 3i Atlas reflects both our capabilities and our limitations. we've conducted extraordinary observations across the electromagnetic spectrum using humanity's most advanced instruments. We've coordinated international campaigns bringing together professional and amateur astronomers. We've generated terabytes of data that will fuel research for years. But we've also stumbled. Data locked away for bureaucratic reasons, observations delayed by political shutdowns, scientists forced to work around obstacles that have nothing to do with astronomy. These failures are correctable. We can do better next time. We must do better next time, because the next time is coming. The fourth interstellar visitor will arrive. Maybe next year, maybe in 5 years, maybe next month. We can't predict when or where in the sky it will appear, but we know it's out there, right now, moving through the galaxy on its own long journey, and someday, somewhere, it will pass close enough to our sun for us to detect it. And when that happens, we'll have another chance, another cosmic messenger bringing news from stellar systems we'll never visit, another opportunity to expand our understanding of galactic diversity, another test of our ability to recognize the truly strange when it appears in our data. Will the fourth visitor be similar to 3I Atlas? Probably not. The first 3 interstellar objects were completely different from each other. The fourth will almost certainly be different from all 3. It might be smaller or larger, faster or slower, darker or brighter, more active or less active. It might fragment spectacularly or hold together stoically. It might have yet another impossible property that none of the previous visitors exhibited, and we'll observe it carefully, analyse it thoroughly, and be surprised repeatedly. Because that's the pattern. That's what interstellar visitors do. They arrive carrying secrets from conditions we don't understand, exhibit behaviours we can't predict, and force us to revise our cosmic worldview. This is the future of interstellar object astronomy. A new field born from the realization that the space between stars is not empty, but filled with wandering fragments from countless stellar systems. Each fragment tells a different story. Each one expands our understanding. Each one reminds us how limited our perspective has been. 3I Atlas is not an ending, it's a beginning. The beginning of a new chapter in humanity's relationship with the galaxy. We're learning to read the messages written in cosmic debris, slowly, imperfectly, but with increasing skill. The comet is fading now. Every night it gets a little dimmer as it moves farther from the sun and Earth. Soon, it will be beyond the reach of even our largest telescopes. The bright coma will fade into the background darkness. The jets will disperse into the interplanetary medium. The nucleus will become just another invisible speck drifting through the void. But the data remains. The images, the spectra, the measurements. The record of those few months when an ancient wanderer from another star system passed through our neighbourhood and allowed us to study it. That record is permanent, and it will continue yielding insights long after the comet itself has vanished. Years from now, researchers will still be analysing 3I Atlas observations, finding patterns that current analysis misses, making connections that require broader context from future discoveries. The data we're gathering now feeds not just immediate understanding, but long-term comprehension. This is the gift that interstellar visitors bring. Not just momentary wonder, but lasting knowledge. Not just pretty pictures, but fundamental insights. Not just one object's properties, but hints about the broader galactic environment we inhabit. And the most important insight of all? We don't know what we don't know. The galaxy is stranger than we imagined. Matter can organise itself in ways we haven't predicted. Physics allows behaviours we haven't modelled, and the debris field between stars is far more complex and diverse than one solar system could ever teach us. 3I Atlas, with its bleeding nickel vapour and its impossible anti-tail, and its 12 documented anomalies and its structural resilience, is proof of that complexity. It came from conditions we don't fully understand. It exhibits properties we can't fully explain. And it's leaving us with questions we may never completely answer. But it came. It allowed us to see it. and it changed our understanding of what's possible in the cosmic ocean that surrounds our tiny solar system island. That change is permanent. Even after the comet fades from view, even after the telescopes move on to other targets, even after the excitement subsides, we'll remember what we learned. That interstellar space is filled with ancient wanderers carrying secrets from stellar environments we'll never visit. That each visitor is unique, strange in its own way, impossible to predict from theory alone. That the universe takes delight in violating our expectations, and that the galaxy, vast and ancient and filled with processes we barely comprehend, is sending us messengers, one by one, fragment by fragment, teaching us in the only way it can that reality is always larger and stranger than our theories allow. 3i Atlas is one such messenger. But to fully understand what this messenger is telling us, we must first understand the broader context of comets themselves, where they come from, how they form, what they're made of, and why some, like this ancient wanderer, end up drifting between the stars. The story of 3i Atlas cannot be fully understood without understanding the broader context of comets in our solar system and throughout galactic history. To truly grasp what makes this interstellar visitor so unusual, we must first explore the ordinary. We must examine the comet populations that call our solar system home, the objects that have been circling our sun for billions of years, carrying the chemical fingerprints of our own stellar neighbourhood's formation. Our solar system contains two vast reservoirs of cometary material. Both were born during the chaotic early days when planets were still forming and gravitational dynamics were reshaping the architecture of our cosmic neighbourhood. Understanding these reservoirs provides essential context for recognising what makes interstellar comets, like 3i Atlas, fundamentally different from their locally born cousins. The first reservoir lies beyond Neptune's orbit in a flattened disc-shaped region called the Kuiper Belt. This structure extends from about 30 astronomical units from the Sun, just beyond Neptune, to approximately 50 astronomical units. To put that in perspective, Earth orbits at 1 astronomical unit from the Sun. Neptune sits at 30 astronomical units. The Kuiper Belt begins where Neptune's gravitational influence starts to fade and extends into the outer darkness, where solar energy becomes almost negligible. The Kuiper Belt is not empty space punctuated by occasional rocks. It's a cosmic graveyard containing the leftover building blocks of planet formation. When the solar system was young, when the sun had just ignited and the planets were still accreting from the protoplanetary disk, this region was far more densely populated. Scientists estimate that the original Kuiper Belt contained 7 to 10 times Earth's mass in solid material. Countless small bodies, planetesimals, dwarf planets, and protoplanetary objects circled in the outer reaches, where temperatures were cold enough for volatile ices to remain frozen. But planetary migration changed everything. As Jupiter, Saturn, Uranus, and Neptune achieved their current masses, their immense gravitational fields began reshaping the orbits of everything around them. Computer simulations suggest that the giant planets didn't form in their current locations. Jupiter likely migrated inward slightly while Saturn, Uranus, and Neptune moved outward, driven by gravitational interactions with the debris disk. This migration was catastrophic for the Kuiper Belt population. As Neptune moved outward, its gravity scattered objects like a cosmic billiard break. Some were flung into the inner solar system where they became short-period comets. Others were ejected entirely into interstellar space. Most of the original mass was lost. What remains today is a ghost of the original structure. The modern Kuiper Belt contains perhaps 10% of Earth's mass, maybe less. But that remnant still harbours fascinating objects. Pluto, once considered the 9th planet, is actually one of the largest Kuiper Belt objects. Its diameter of about 2,280 kilometres makes it king of the region, though it shares that realm with other substantial bodies like Eris, Makemake, and Haumea. Eris deserves special mention because its discovery in 2005 triggered the debate that led to Pluto's reclassification as a dwarf planet. Eris is slightly more massive than Pluto and orbits the Sun in a highly elliptical path that takes 557 years to complete. Its surface is covered in methane ice that appears bright and reflective in telescopic observations. The discovery of an object comparable to or larger than Pluto forced astronomers to confront an uncomfortable question. If Pluto is a planet, why isn't Eris? And if we call Eris a planet, what about the dozens or hundreds of similar objects likely waiting to be discovered in the outer solar system? The International Astronomical Union's controversial decision to define a planet as an object that has cleared its orbital neighbourhood meant that Pluto, sharing its region with thousands of similar bodies, no longer qualified. But the Kuiper Belt contains more than just large dwarf planets. Thousands of smaller objects have been catalogued, ranging from hundreds of kilometres down to the detection limits of our best telescopes. These Kuiper Belt objects, often called KBOs, come in several distinct families based on their orbital characteristics. The classical Kuiper Belt objects maintain fairly circular orbits aligned with the plane of the planets. The resonant objects are locked in gravitational resonances with Neptune, orbiting at precise ratios like 3 times for every 2 Neptune orbits or 2 times for every 1. The scattered disk objects follow highly eccentric elliptical paths, likely scattered by close encounters with Neptune in the distant past. Each of these populations tells part of the story of early solar system dynamics. The classical KBOs represent material that formed in place and was never strongly perturbed. The resonant objects were captured into stable gravitational relationships as Neptune migrated. The scattered disk bodies are refugees from catastrophic encounters that sent them careening into the outer darkness on orbits that barely remain bound to the Sun, and occasionally one of these Kuiper Belt objects gets perturbed into an orbit that brings it into the inner solar system. When that happens, as the object approaches the Sun and warms, its frozen volatile ices begin to sublimate. Water vapour, carbon monoxide, carbon dioxide, methane, ammonia, all the compounds that remain frozen in the frigid outer regions start transitioning directly from solid to gas. This outgassing creates the characteristic coma and tail that make comets so visually spectacular. These are short-period comets, objects with orbital periods typically less than 200 years, often much less. They make repeated passages through the inner solar system, gradually depleting their volatile reserves until eventually they become inert rocky nuclei indistinguishable from asteroids. Comet Halley is perhaps the most famous short-period comet, though its 76-year orbital period actually places it in a transitional category between short and long-period comets. Edmund Halley's recognition in 1705 that the comets observed in 1531, 1607 and 1682 were actually the same object returning periodically was a revolutionary insight. It demonstrated that comets followed predictable orbits governed by the same gravitational laws that controlled planetary motion. When the comet returned as predicted in 1758, 16 years after Halley's death, it validated his calculations and transformed comets from unpredictable omens into objects of scientific study. Halley's comet continues to return like clockwork. Its most recent perihelion occurred in 1986, providing the first opportunity for spacecraft to visit a comet. The European Space Agency's Giotto probe came within 596 kilometres of the nucleus, capturing close-up images of a dark, peanut-shaped body about 15 kilometres long. The nucleus was far darker than expected, reflecting only about 4% of incident sunlight. Its surface appeared ancient and battered, covered in impact craters and hills. Jets of gas and dust erupted from specific locations on the sunward side, where volatile ices were being heated and vaporized. These observations revolutionized our understanding of cometary nuclei, revealing them to be far more complex than the simple, dirty snowball model had suggested. but the Kuiper belt, vast as it is, represents only the inner reservoir of cometary material. Beyond it, at distances so immense that even the Sun appears as nothing more than a bright star, lies the Oort cloud. This spherical shell of icy bodies surrounds the entire solar system like a cosmic cocoon. Its inner edge begins somewhere around 2,000 astronomical units from the Sun, where the Kuiper belt's scattered disk fades into the interstellar void. Its outer boundary may extend as far as 100,000 astronomical units, nearly halfway to the nearest star. At those distances, the Sun's gravitational influence becomes almost imperceptible. An object at 50,000 astronomical units orbiting the Sun takes roughly 10 million years to complete a single orbit. The orbital velocities are measured in meters per second rather than kilometers per second. These objects are barely bound to our solar system at all, held in place by the most tenuous gravitational threads. The Oort cloud's existence was first proposed by Dutch astronomer Jan Oort in 1950 as an explanation for the observed properties of long-period comets. These comets appear from random directions in the sky, on orbits that take hundreds, thousands, or even millions of years to complete. Their trajectories often bring them plunging toward the Sun from the most extreme distances, suggesting they originate from a spherical reservoir rather than the flattened disk of the Kuiper belt. Oort's calculations indicated that a vast population of icy bodies must exist in the outermost reaches of the solar system, occasionally perturbed by passing stars or galactic tides into orbits that carry them into the inner system where we can observe them. We have never directly observed an Oort cloud object in its native environment. The distances are simply too vast and the objects too small and dark. But the indirect evidence is overwhelming. Dozens of long-period comets are discovered every year, each one following an orbit that traces back to the distant outer reaches of the solar system. The orbits show no preference for the plane of the planets, confirming the spherical distribution Oort predicted. And the sheer number of long-period comets implies a source population numbering in the trillions of objects. How did the Oort cloud form? The most widely accepted model suggests it's another legacy of early planetary migration. During the chaotic period when the giant planets were reshaping the solar system's architecture, countless small bodies were scattered in all directions. Some were ejected completely, escaping the Sun's gravity and becoming interstellar wanderers. Others were flung to extreme distances but retained just enough orbital energy to remain bound. These objects settled into the vast spherical shell we call the Oort cloud, a repository of pristine material preserving the chemical conditions of the early solar system. The Oort cloud objects are time capsules. They formed 4.6 billion years ago in the protoplanetary disk and have remained frozen ever since, barely touched by the feeble sunlight that reaches their distant orbits. When one is perturbed into the inner solar system and becomes a visible comet, we're seeing material that has been preserved unchanged since the solar system's formation. The chemical composition of these comets tells us about the temperature, pressure, and element abundances in different regions of the ancient protoplanetary disk. But here's what makes the Oort cloud profoundly unsettling. We cannot see it. We cannot directly observe it. We infer its existence from the comets it occasionally sends our way, but the cloud itself remains invisible, a vast dark structure encompassing our entire solar system that we must accept on faith based on indirect evidence. And that invisible structure defines the true boundary of our solar system far beyond the planets we can easily see. Voyager 1, humanity's most distant spacecraft, crossed into interstellar space in 2012 after travelling for 35 years. It had passed beyond the heliosphere, the bubble of solar wind that surrounds the inner solar system. But even Voyager 1, now more than 160 astronomical units, from the Sun, has barely begun its journey through the Oort cloud. At its current velocity of about 17 kilometers per second, Voyager 1 won't reach the inner edge of the Oort cloud for another 300 years. Passing through the cloud entirely will take another 30,000 years, Only then will the spacecraft truly leave our solar system behind and enter the unambiguous realm between stars. This context is crucial for understanding interstellar visitors like 3I Atlas. That comet didn't originate from our Kuiper belt or Oort cloud. It formed around a different star entirely, under different conditions, with different chemical abundances and temperatures. It was ejected from its home system and has been wandering through interstellar space ever since, possibly for billions of years. Its composition reflects the protoplanetary disk of another stellar system, potentially one that formed when the galaxy was younger and chemically different from today. Comparing 3I Atlas to solar system comets is like comparing a message in a bottle that washed up from across an ocean to shells you find on your local beach. They're both products of marine environments, but they come from completely different ecosystems with their own unique characteristics. The shells from your beach tell you about local conditions, local biology, local chemistry. The message in a bottle tells you about somewhere else entirely, somewhere you may never visit, somewhere that might operate according to different principles. And that's what makes interstellar comets so scientifically valuable. Everyone is a sample from a different stellar environment. Everyone carries information about planetary system formation under conditions that might differ radically from our sun's circumstances. Our theories of how planets form are built primarily from observations of one system, ours. We've detected thousands of exoplanets around other stars, but those observations mostly tell us about massive planets orbiting close to their stars, the ones easiest to detect with current methods. We know very little about the small bodies, the comets and asteroids and debris in other stellar systems. Interstellar visitors bridge that knowledge gap. They bring us samples from those distant systems, not large enough to be planets, but substantial enough to carry detailed chemical information. And when we study them carefully, measuring their composition and structure and behaviour, we're learning about the diversity of planetary system formation across the galaxy. This is why the differences between Oumuamua, 2I Borisov and 3I Atlas are so scientifically important. They're not just interesting anomalies, they're data points revealing the range of outcomes possible in planetary system formation. Oumuamua's extreme elongation tells us something about how objects can evolve under certain conditions. 2I Borisov's high carbon monoxide suggests formation around a dimmer, cooler star than our Sun. 3I Atlas's carbon dioxide, dominance and nickel vapour indicate yet another set of formation conditions, possibly around an ancient star with different metallicity than younger systems. But to fully appreciate these interstellar visitors, we must also understand the most spectacular comets our own solar system has produced. Because while 3I Atlas is unusual, it's not the only comet to ever violate expectations or surprise astronomers with unexpected behaviour. Consider Comet Hale-Bopp, which graced Earth's skies in 1997 and became one of the most widely observed comets in human history. Discovered independently by Alan Hale and Thomas Bopp in July 1995, the comet was remarkable from the beginning, because it was detected at an enormous distance of 7.2 astronomical units from the Sun, beyond Jupiter's orbit. Most comets aren't discovered until they're much closer, and their activity has made them bright enough to spot easily. But Hale-Bopp was so intrinsically large and active that it could be seen even at that tremendous distance. As the comet approached the Sun over the next 18 months, it brightened steadily and developed spectacular tails that became visible to the naked eye by early 1997. At its peak in March and April 1997, Hale-Bopp was so bright it could be seen from light-polluted urban areas, a rarity for comets which usually require dark skies for good viewing. The comet displayed two prominent tails, one bluish and composed primarily of ionized gas, the other yellowish-white and made of reflected sunlight from dust particles. These dual tails, visible in even modest binoculars, made Hale-Bopp one of the most photogenic comets ever observed. But what made Hale-Bopp scientifically significant was its size and composition. Estimates suggest the nucleus is about 60 kilometers in diameter, roughly 4 times the diameter of Halley's Comet, and making it one of the largest cometary nuclei ever measured. This enormous size meant the comet produced prodigious amounts of gas and dust as it warmed. At peak activity, Hale-Bopp was releasing about 300 tons of material per second into space. That's 300,000 kilograms every second, more mass than a fully loaded 747 aircraft, being continuously ejected from the nucleus through sublimation of its ices. Spectroscopic observations of Hale-Bopp revealed an unusually rich chemical composition. In addition to the expected water vapour, carbon dioxide and carbon monoxide, astronomers detected numerous complex organic molecules including methane, ethane, methanol, formaldehyde, and even traces of more complex compounds. The detection of deuterium, a heavy isotope of hydrogen, allowed researchers to measure the comet's DH ratio, which provides clues about the temperature and conditions where its ices formed. Hale-Bopp's DH ratio suggested formation in a very cold environment, consistent with origin in the outer regions of the protoplanetary disk, or possibly even the Oort cloud. One of the most unexpected discoveries was the detection of argon gas in Hale-Bopp's coma. Argon is a noble gas that doesn't easily form chemical compounds, and its presence implied that the comet's nucleus had trapped argon molecules in its ices during formation. This trapping requires extremely cold temperatures, below about 30 Kelvin, suggesting that at least some of Hale-Bopp's material formed in the coldest regions of the protoplanetary disk, or incorporated material from the pre-solar molecular cloud that collapsed to form our solar system. Hale-Bopp also displayed unusual activity patterns. Unlike many comets that show steady brightening and dimming as they approach and recede from the Sun, Hale-Bopp exhibited irregular outbursts where its brightness suddenly increased for periods of days to weeks. These outbursts likely resulted from the exposure of fresh, volatile, rich material as surface layers sublimated away, or from the breakup of subsurface ice pockets that suddenly vented their contents into space. Such behaviour demonstrates that cometary nuclei are not uniform frozen balls, but rather complex structures with varying compositions and strengths in different regions. The comet's orbit revealed that Hale-Bopp was making only its second or possibly third passage through the inner solar system. Its previous orbital period was approximately 4,200 years, meaning the last time it approached the Sun, human civilization was just beginning to develop agriculture. Gravitational perturbations from Jupiter during the 1997 passage altered the orbit, changing the period to about 2,533 years. This means Hale-Bopp won't return to the inner solar system until roughly the year 4530, long after everyone currently alive has died and turned to dust. The comet's tremendous size and relatively pristine state, having made so few solar passages, meant that Hale-Bopp provided an excellent window into the composition of Oort cloud material. Unlike short-period comets that have been baked by numerous close solar encounters, degrading and depleting their volatile inventories, Hale-Bopp remained chemically fresh, still retaining the volatile compounds that formed billions of years ago. But if Hale-Bopp represents a majestic visitor from the outer reaches of our solar system, Comet Shoemaker-Levy 9 represents something far more violent: a comet's death. In March 1993, astronomers Carolyn and Eugene Shoemaker and David Levy discovered an unusual comet orbiting Jupiter rather than the Sun. Follow-up observations revealed something unprecedented. The comet had been captured by Jupiter's gravity during a close approach decades earlier and had been orbiting the giant planet ever since. But during a particularly close pass in July 1992, Jupiter's immense gravitational field had torn the comet apart through tidal forces. Instead of a single nucleus, Shoemaker-Levy 9 now consisted of at least 21 distinct fragments strung out in a line, resembling pearls on a cosmic necklace. Orbital calculations revealed something even more remarkable. The fragments were on a collision course with Jupiter. In July 1994, the pieces would impact the giant planet's atmosphere in the most spectacular astronomical event since the invention of the telescope. For the first time in human history, we would witness a cosmic collision between two solar system bodies, an impact energetic enough to be visible across the entire Earth-Jupiter distance of over 600 million kilometers. The scientific community mobilized every available telescope. Ground-based observatories, Hubble Space Telescope, the Galileo spacecraft which was approaching Jupiter, even radio telescopes, all turned their attention to the giant planet. The world watched as, over the course of 6 days from July 16th to 22, 1994, the fragments slammed into Jupiter's southern hemisphere at velocities exceeding 60 kilometers per second. Each impact released energy equivalent to millions of megatons of TNT. The largest fragments created fireballs that briefly outshone Jupiter's entire normal emission. These fireballs rose thousands of kilometers above the cloud tops before collapsing back down, creating dark impact scars visible in amateur telescopes from Earth. The largest scar from the impact of fragment G grew to be larger than Earth's diameter and remained visible for months as Jupiter's atmospheric winds slowly dispersed the debris. The impacts provided an unprecedented opportunity to study Jupiter's atmospheric composition. Material from deep within the atmosphere was excavated and thrown into view, revealing compounds normally hidden beneath the visible cloud layers. Spectroscopic analysis detected water, ammonia, carbon disulfide, and complex organic compounds thrown up from the depths. The energy released by the impacts also created chemical reactions that produced new compounds not normally present in Jupiter's atmosphere. But beyond the spectacular images and the scientific data about Jupiter's atmosphere, Shoemaker-Levy 9 taught us something profound about cosmic violence. The comet had likely been orbiting Jupiter for decades, possibly since the 1960s or 70s. During that time, it was slowly spiraling inward due to gravitational perturbations. The July 1992 close approach brought it within Jupiter's Roche limit, the distance at which tidal forces become stronger than the object's self-gravity. At that point, fragmentation became inevitable. This process, tidal disruption, is not unique to Shoemaker-Levy 9. It happens throughout the universe whenever a smaller body ventures too close to a massive one. Asteroids that pass too close to planets can be torn apart. Comets grazing too near to stars fragment into pieces. Even stars that wander too close to supermassive black holes get shredded by tidal forces, creating spectacular tidal disruption events visible across intergalactic distances. The lesson from Shoemaker-Levy 9 is that the universe is not a peaceful place. Gravity is not a gentle force guiding objects along elegant orbits. It can be violent, destructive, capable of ripping objects apart and sending their fragments on collision courses that release energies beyond human comprehension. The fact that we happened to be watching with our most advanced instruments when this particular collision occurred was extraordinarily fortunate. It won't happen again in our lifetimes. Jupiter captures comets occasionally, perhaps once per decade or century, but most simply orbit the planet for a while before being ejected back into solar orbits. Only rarely does one spiral inward far enough to fragment and impact. Yet Shoemaker-Levy 9 was also a reminder of Earth's vulnerability. If a 20-fragment comet train could hit Jupiter, a planet protected by its enormous gravity well in distance from the inner solar system, what about Earth? What about the possibility of a comet or asteroid on a collision course with our world? The impacts on Jupiter occurred just 3 years after the publication of a landmark study that identified the Chicxulub crater in Mexico as the site where an asteroid impact 66 million years ago caused the extinction of the dinosaurs. The connection was impossible to ignore. The craters on Jupiter's clouds, each one larger than Earth, were stark reminders of what such impacts can do. If a 10-kilometer asteroid could end the age of dinosaurs and fundamentally reshape Earth's biosphere, what could a comet nucleus do? This concern has driven the development of near-Earth object detection programs designed to catalogue asteroids and comets that might pose impact risks. The statistics are sobering. Earth is hit by small meteoroids constantly, most burning up harmlessly in the atmosphere. Objects around 1 meter in diameter strike roughly once per year, usually over oceans or unpopulated areas. 10-meter objects, large enough to cause regional damage, hit approximately once per century. The 2013 Chelyabinsk meteor that injured 1,500 people in Russia was about 20 meters in diameter. Objects large enough to cause global catastrophe, like the Chicxulub impactor, strike on timescales of tens of millions of years. But comets add uncertainty to these statistics. Unlike asteroids, which mostly orbit in the predictable asteroid belt between Mars and Jupiter, comets can appear from any direction with very little warning. Long-period comets arriving from the Oort cloud might only be detected months before potential impact, far too little time for any mitigation efforts, and comets travel faster than asteroids, having fallen inward from the outer solar system and picked up tremendous velocity. This higher speed means greater impact energy. A 5-kilometer comet hitting Earth would release significantly more energy than a 5-kilometer asteroid. The good news is that large comet impacts are extremely rare. The bad news is that they're not impossible. Shoemaker-Levy 9 demonstrated that the universe contains enough violence to tear apart and destroy worlds. Jupiter took those impacts. Someday, perhaps hundreds of millions of years from now, Earth might face a similar threat. Or it might be tomorrow. We can't know until we develop better detection systems and maintain constant surveillance of the sky. These stories, Hale-Bopp's majestic brilliance and Shoemaker-Levy 9's violent end, provide essential context for appreciating comets, not just as beautiful celestial objects, but as archives of solar system history and reminders of cosmic danger. They also help us understand why astronomers get so excited about interstellar visitors. If comets from our own Oort cloud can display such diverse properties and behaviours, what might comets from other stellar systems reveal? But understanding the objects themselves is only half the story. We must also understand how we observe them, how we gather the data that allows us to decode their secrets. The technology of astronomical observation has advanced dramatically in recent decades, and that technological revolution has made the detection and study of objects like 3I Atlas possible. Consider the challenge of finding a small, dark, fast-moving object millions of kilometers away. The typical comet nucleus is only a few kilometers across. At a distance of hundreds of millions of kilometers, it subtends an angle measured in milliseconds, far below the resolution limit of optical telescopes, but just bright enough to be detectable if you know where to look. But you don't know where to look because the object is moving against the background stars, and its trajectory is unpredictable until you've observed it multiple times to establish an orbit. This is where automated survey systems become essential. The Atlas system that discovered 3I Atlas consists of 4 telescopes located at different sites around the world in Hawaii, Chile, and South Africa. Each telescope scans large sections of the sky repeatedly, taking images every few nights. Computer algorithms compare the images, looking for objects that have moved between observations. Anything that shifts position is flagged for follow-up analysis. Most detections turn out to be known asteroids following predictable orbits. But occasionally, the system finds something new. The Atlas telescopes aren't particularly large by modern standards. The primary mirrors are only about 50 centimeters in diameter, roughly the size of a decent amateur telescope. But what they lack in light-gathering power they make up for in field of view. Each telescope can image several square degrees of sky at once, allowing rapid surveys of large areas. The key is coverage and cadence. By imaging the same regions repeatedly and comparing the results, the system can detect even faint objects that would be invisible in a single image. Once an object is detected and flagged as potentially interesting, larger telescopes take over. These follow-up observations are crucial for determining the object's orbit precisely enough to predict where it will be, days, weeks, or months into the future. For 3I Atlas, follow-up observations came from multiple sources. The Zwicky Transient Facility in California provided additional position measurements. Telescopes in Spain, Italy, and other countries contributed data. Within days, astronomers had enough observations to confirm the hyperbolic trajectory and interstellar origin. But confirmation of interstellar origin is just the beginning. The real scientific work involves characterizing the object's physical properties. This requires spectroscopy, the analysis of light broken down into its component wavelengths. Every atom and molecule absorbs and emits light at characteristic wavelengths determined by quantum mechanics. By measuring which wavelengths are present or absent in light coming from the comet, we can identify which chemical species are present in its coma. Spectroscopy is extraordinarily powerful but technically challenging. The light from a faint comet is dim to begin with. Spreading that light out across a spectrum makes it dimmer still, requiring long exposure times on large telescopes. And you need high spectral resolution to distinguish between different molecular species that emit at similar wavelengths. The Very Large Telescope in Chile, which detected the nickel vapor around 3I Atlas, uses a spectrograph called UVUS, the ultraviolet and visual Echelle spectrograph. This instrument can spread light across a spectral resolution of about 80,000, meaning it can distinguish wavelengths that differ by only one part in 80,000. At this resolution, individual molecular emission lines are clearly separated, allowing unambiguous identification of chemical species. The nickel detection itself required careful analysis. Nickel atoms in the gas phase emit light at specific ultraviolet and optical wavelengths when excited by solar radiation. The UV's data showed clear emission features at exactly the wavelengths expected for nickel, features that couldn't be produced by any other common element. The surprise was not just detecting nickel, but detecting it at a distance from the Sun where the temperature should be far too cold for nickel to vaporize. James Webb Space Telescope's observations employ different techniques. Webb doesn't observe invisible light at all. It's an infrared telescope sensitive to wavelengths longer than what human eyes can see. This infrared sensitivity is perfect for studying molecules like carbon dioxide, which have strong absorption and emission features in the infrared. Webb's near-infrared spectrograph, NIRSpec, split the comet's infrared light into a spectrum revealing the dominant presence of CO2 and allowing measurement of its abundance relative to other species. Infrared observations have another advantage. Dust particles in the comet's coma, which scatter visible light and can obscure spectroscopic features, are much less problematic in the infrared. This allows clearer views of the gas composition without dust contamination confusing the results. Hubble Space Telescope contributed visible light imaging that revealed the comet's coma structure and provided constraints on nucleus size. Hubble's Wide Field Camera 3 has exceptional sensitivity and resolution, allowing it to detect faint extended structures around the bright nucleus. The teardrop-shaped coma visible in Hubble images results from the combination of outgassing from the nucleus and solar radiation pressure pushing the dust particles away from the Sun. But perhaps the most challenging observations were those attempted by Mars orbiters during 3I Atlas's October 3rd flyby of the Red Planet. The Mars Reconnaissance Orbiter's HiRISE camera is designed for imaging Mars's surface, not distant astronomical objects. Its field of view is narrow, optimized for high-resolution imaging of small areas rather than wide-angle sky surveys. Pointing it at a fast-moving comet millions of kilometers away required careful planning and precise timing. The HiRISE team had to predict exactly where the comet would be at the time of observation, taking into account uncertainties in the orbit and the comet's position. They had to orient the spacecraft to point the camera in the right direction while maintaining stable attitude control, and they had to time the observations precisely because the comet was moving across HiRISE's narrow field of view at a rate that would carry it out of frame within minutes. The fact that these observations succeeded at all is a testament to the sophistication of modern spacecraft operations. The images, when they're finally released, will represent some of the highest resolution views of an interstellar object ever obtained. At a distance of 29 million kilometers, HiRISE's 50-centimeter primary mirror should achieve a spatial resolution of about 30 kilometers per pixel. That's not enough to resolve the nucleus directly unless it's at the upper end of size estimates, but it's sufficient to reveal details of the coma structure and potentially constrain the nucleus size based on how concentrated the brightness peak is. These technological capabilities, from automated survey telescopes to giant space observatories to Mars orbiters repurposed for astronomical targets, represent the culmination of centuries of astronomical instrument development. Galileo's first telescopic observations in 1609 revealed Jupiter's moons and Saturn's rings, but could barely resolve planetary disks. Modern instruments can detect individual molecules in the atmospheres of planets orbiting other stars, image the event horizons of supermassive black holes, and track objects moving through interstellar space at velocities exceeding 200,000 kilometers per hour. But these capabilities also reveal how much we still don't know. Every technological advance opens new windows on the universe and reveals new mysteries. Before automated survey systems, we detected perhaps one interstellar object per decade, if that. Now we're detecting several per decade and expect that rate to increase dramatically as new facilities come online. The Vera C. Rubin Observatory, currently in final testing in Chile, will revolutionize transient astronomy when it begins full operations. Its 8.4-meter primary mirror and massive 3,200 megapixel camera will image the entire visible sky every few nights, detecting anything that moves, changes, or appears newly in any image. Conservative estimates suggest Rubin will detect one interstellar object per month. Optimistic projections go as high as several per week. Think about what that means. Within a decade, we might have catalogues of hundreds of interstellar visitors. We'll see comets from red dwarf systems, debris from giant planet systems, fragments from stellar collisions. We'll observe carbon-rich objects, nitrogen-rich objects, water-dominated objects, rocky objects, metallic objects, possibly even objects with compositions we've never imagined. Each one will add a data point to our understanding of planetary system diversity across the galaxy. But increased detection also means increased challenges. With hundreds of interstellar objects to study, we can't give each one the intensive observational campaign that 3i Atlas received. Priorities will have to be set. Which objects are scientifically most valuable? Which deserve follow-up spectroscopy with large telescopes? Which are worth missions like Comet Interceptor, the European Space Agency's planned spacecraft designed to rendezvous with a long-period comet or interstellar visitor? These decisions will require rapid assessment of newly detected objects. Within days of discovery, astronomers will need to determine the object's trajectory, estimate its size and activity level, and make preliminary assessments of its composition based on colours and brightnesses. The most interesting objects, those with unusual properties or trajectories that bring them especially close to Earth, or other targets of interest, will receive intensive follow-up. Others will be catalogued and archived but not studied in detail. This triage is inevitable when dealing with rare events that suddenly become common. In medicine, when a rare disease suddenly becomes prevalent, doctors must quickly develop protocols for diagnosis and treatment prioritization. In astronomy, as interstellar objects transition from once-per-decade curiosities to monthly occurrences, we must develop similar protocols for study prioritization. But even with hundreds of detections, each interstellar visitor remains scientifically precious. Because unlike asteroids or comets from our solar system, which we can study at leisure knowing more will always be available, interstellar objects are one-time opportunities. Each one passes through once and never returns. The data we gather during that brief passage is all we'll ever have. There are no do-overs, no chances for improved observations years later when better instruments become available. This is why the high-rise image delay is so frustrating to researchers. The observations were made, the data exists, but it's locked away during the brief window when it could inform follow-up observations, while the comet is still bright enough to study. Once 3i Atlas fades below detectability, those images become historical rather than actionable. They'll still have scientific value for detailed analysis and comparison with other observations, but they can't guide real-time observing strategies anymore. The experience with 3i Atlas will inform how future interstellar visitors are handled. Ideally, protocols should be established ensuring rapid data release for time-critical observations. The scientific value of these objects is too high, and the opportunities too fleeting to allow bureaucratic delays. But establishing such protocols requires coordination across international agencies and balancing the legitimate needs for data quality control against the urgency of rapid release. As we develop better detection systems and observe more interstellar visitors, patterns may emerge. Perhaps objects from red dwarf systems consistently show high carbon monoxide abundances. Perhaps metal-rich stars produce comets with unusual mineral compositions. Perhaps stellar systems in the galactic halo, with lower metallicity, produce compositionally distinct objects compared to systems in the galactic disk. These patterns, if they exist, would tell us about the relationship between stellar properties and planetary system composition. They would allow us to predict what types of planets might orbit different types of stars based on the chemical signatures visible in their cometary debris. They would provide ground truth for theoretical models of planet formation under various stellar conditions, but we might not find clear patterns. The diversity we've already seen in just 3 interstellar objects suggests that planetary system formation is even more variable than models predict. Perhaps every stellar system is unique in ways that produce distinctive chemical signatures in injected material. Perhaps the scattering properties is so large that clear relationships between stellar type and comet composition remain elusive even with hundreds of samples. Either outcome is scientifically valuable. Finding patterns would validate our theoretical understanding and provide predictive power. Finding chaos would force us to confront the limitations of our models and recognize that planetary system formation involves too many variables and contingencies to be easily reduced to simple rules. The story of comets, both those from our solar system and those arriving from interstellar space, is ultimately a story about cosmic recycling. Stars form from molecular clouds, condense into fusion reactors surrounded by protoplanetary disks, produce planets and smaller bodies, shine for billions of years, and eventually die. When they die, they return their material to the interstellar medium, sometimes gently through stellar winds, sometimes violently through supernovae. That material mixes with other clouds, gets incorporated into new stars, creates new planetary systems. The cycle continues, generation after generation of stars, each one slightly different from the last as the galaxy's chemical composition slowly evolves. Comets are fragments of this cycle. They formed in protoplanetary disks when stars were young. Most remained bound to their parent stars, orbiting for billions of years in asteroid belts or comet clouds. But some, through gravitational perturbations, were ejected into interstellar space. These wanderers carry the chemical fingerprints of their birth systems as they drift through the galaxy, occasionally passing through other stellar systems before continuing their lonely journeys. When one of these wanderers passes through our solar system, we're seeing a messenger from another branch of the galactic family tree. It formed around a different star, under different conditions, at a different time in galactic history. It carries information about those distant circumstances, encrypted in its chemical composition and physical properties. By studying it carefully, we decode that information and learn something about the galaxy beyond our immediate neighbourhood. This perspective transforms how we think about space. The void between stars is not empty. It's filled with refugees from dead systems, fragments of worlds that no longer exist, messengers from stellar environments we'll never observe directly. Each fragment carries a story, and the galaxy is filled with billions of such stories, most of which will never be heard because the objects carrying them will never pass close enough to any observers to be detected and studied. We're fortunate to live in an era when our technology has advanced to the point where we can detect and study these cosmic wanderers. A century ago, interstellar objects were purely theoretical. 50 years ago, they might have been detectable but would have been difficult to distinguish from ordinary comets. Today, we can identify them within days of discovery, characterize their compositions, measure their trajectories and learn from them. But our current capabilities are just the beginning. Future observatories will be even more sensitive. Spacecraft will eventually be fast enough to intercept interstellar visitors and perform close-up studies. Perhaps within our lifetimes, a probe will match velocities with an interstellar comet, fly alongside it, sample its coma directly, possibly even land on the nucleus and analyze its composition in detail. Such a mission would represent a watershed moment in astronomy, bringing back direct samples from another stellar system without requiring the centuries of travel time that interstellar travel would demand. Until that day arrives, we study interstellar visitors from afar. We point our telescopes toward them. We split their light into spectra. We measure their trajectories and sizes and activity levels. We gather every photon we can and extract every bit of information those photons carry. And slowly, observation by observation, object by object, we build up a picture of the galaxy beyond our solar system, one cosmic wanderer at a time. 3i Atlas is one chapter in this emerging story. Its nickel vapor and carbon dioxide dominance and structural integrity and anti-tail all contribute to our understanding of what's possible in the cosmic ocean that surrounds us. The comet is teaching us lessons we couldn't learn any other way because it carries information from a place we cannot reach. And the lessons continue, even as the comet fades from view, even as it becomes too distant and dim for further observations, the data remains. Years from now, researchers will still be analysing 3i Atlas measurements, comparing them with future interstellar visitors, using them to constrain models of planetary system formation and galactic chemical evolution. The comet's brief passage through our neighbourhood will contribute to human knowledge long after the object itself has disappeared back into the darkness between stars. This is the nature of astronomy. We study objects and events that we cannot touch, cannot visit, cannot experiment upon. We gather light across vast distances and decode the information that light carries. Sometimes that information is clear and unambiguous. More often it's fragmentary and uncertain, requiring careful analysis and interpretation. But even uncertain information is valuable when it's the only information available. The universe is revealing its secrets reluctantly, one photon at a time. Comets like 3i Atlas are part of that revelation, cosmic teachers that arrive unbidden, share what they can, and depart forever. We are the students in this cosmic classroom, trying to learn the lessons before the teacher vanishes and the opportunity is lost. And the fundamental lesson that emerges from studying comets, both local and interstellar, is this: the universe is far more diverse and strange than we imagined. Every confident prediction eventually encounters an observation that doesn't fit. Every model eventually fails when pushed beyond its assumptions. The cosmos delights in surprises, and the scientist's job is to pay attention to those surprises, take them seriously, and revise understanding accordingly. 3i Atlas surprised us with its nickel vapor. It surprised us by surviving perihelion intact. It surprised us with its anti-tail and missing normal tail. Each surprise is a gift, an indication that reality operates according to principles we haven't fully grasped. And while surprises can be frustrating when they undermine confident predictions, they're also what makes science exciting. If we already knew everything, if observations always match predictions perfectly, science would be a dead field with nothing left to discover. But we don't know everything. We're not even close. The universe is vast and old and filled with processes we barely comprehend. Comets are just one small piece of that incomprehensibly large puzzle. but they're a piece we can study, can observe, can learn from. And through that study, we slowly expand the boundaries of human knowledge, one observation at a time, one comet at a time, one photon at a time. The work continues. The telescopes scan the sky. The detectors collect photons. The spectrographs split light into rainbows of information. The computers process the data. And gradually, patiently, the universe reveals itself to those willing to look carefully and think deeply about what they see. 3i Atlas is part of that revelation. One interstellar visitor among many that will eventually be detected. One set of surprising properties among the many surprises yet to come. One chapter in a story that will continue long after we're gone, as future generations of astronomers detect and study the cosmic wanderers that pass through our neighbourhood. The comet doesn't know it's teaching us. It doesn't care about human curiosity or scientific progress. It simply follows its trajectory, a small frozen fragment ejected from a stellar system billions of years ago, wandering through the galaxy according to the same gravitational laws that govern everything else. But from our perspective, trapped in one solar system, dependent on rare visitors to bring us news from beyond, it's precious, a messenger, a teacher, a window into cosmic conditions we'll never experience directly. And for that, for the mere fact of its existence and its passage through our neighbourhood at a time when we have the technology to study it, we should be grateful. Because the universe owes us nothing. It doesn't arrange for convenient teachers or easy lessons. The fact that we're here, now, with instruments capable of detecting and characterising interstellar visitors is an accident of timing that might not have occurred if human civilization had emerged a century earlier or a century later. We're lucky, and we should make the most of that luck by observing carefully, analysing thoroughly, and sharing what we learn freely, so that all of humanity can benefit from the knowledge these cosmic visitors bring. The message continues, the messenger fades, but the knowledge remains, adding to the slowly accumulating store of human understanding about the universe we inhabit. This is the gift of science, transforming fleeting observations into permanent knowledge, converting cosmic accidents into opportunities for learning, turning darkness into light one photon at a time. And in the end, that transformation is what makes us human in the deeper sense. We are the species that looks up, that asks questions, that seeks to understand. We are the observers who bear witness to the universe and record what we see for future generations. We are the inheritors of billions of years of cosmic evolution. Lucky enough to be aware of our cosmic context and curious enough to investigate it. 3i Atlas, with all its mysteries and surprises, reminds us of that heritage. We are children of the cosmos studying the cosmos. We are stardust contemplating stardust. We are the universe becoming aware of itself. And that awareness, that capacity to observe and understand, is perhaps the most precious thing in all of existence. The universe is vast and mostly empty, and largely unconscious. But here, on this small world orbiting an ordinary star, consciousness has emerged. And that consciousness looks outward, seeing what can be seen, learning what can be learned, grateful for every cosmic visitor that brings news from the darkness beyond. This is the legacy we're building, observation by observation. This is the meaning we're creating from cosmic accidents. This is humanity's contribution to the universe, paying attention. The comet recedes into darkness. The telescopes turn to other targets, but the attention remains. We continue watching the sky, waiting for the next messenger, ready to learn whatever lessons it brings. To understand how comets form requires understanding the conditions in protoplanetary disks, those vast clouds of gas and dust that surround newborn stars. When a molecular cloud collapses under its own gravity to form a star, conservation of angular momentum ensures that not all the material falls directly onto the central object. Instead, much of it settles into a rotating disk that extends outward for hundreds of astronomical units. This disk is where planets, asteroids and comets are born. The temperature in a protoplanetary disk varies dramatically with distance from the central star. Close to the star, within a few tenths of an astronomical unit, temperatures can exceed 1500 Kelvin, hot enough to vaporize even refractory materials like iron and rock. At these temperatures, only the most heat-resistant compounds remain solid. This innermost region, sometimes called the hot zone or the terrestrial zone, is where rocky planets like Mercury, Venus, Earth and Mars eventually form. Moving outward, temperatures drop steadily. By about 2 to 3 astronomical units, roughly where the asteroid belt forms in our solar system, temperatures have fallen to perhaps 200 to 300 Kelvin. Water ice can begin to condense at these temperatures, but only in shadowed regions or on the surfaces of larger bodies that can retain volatiles through gravity. This transitional zone marks an important boundary in planetary system formation, sometimes called the snow line or frost line. Inside this boundary, water remains gaseous or liquid. Beyond it, water freezes into solid ice that can be incorporated into growing bodies. Beyond 5 astronomical units, in the realm where Jupiter formed in our solar system, temperatures drop below about 150 Kelvin. At these temperatures, water ice is stable, but so are other volatiles. Carbon dioxide, with a condensation temperature around 70 Kelvin, begins forming solid grains. Methane clathrates, complex structures where methane molecules are trapped in water ice cages, become stable. Ammonia ice can form, though it often exists mixed with water ice rather than as pure crystals. Still farther out, beyond 15 or 20 astronomical units in the coldest regions where comets like 3I Atlas may have formed, temperatures can drop below 50 Kelvin. At these frigid temperatures, even normally gaseous compounds condense into solids. Carbon monoxide, which remains gaseous down to about 25 Kelvin, can freeze onto the surfaces of dust grains. Nitrogen, methane and other volatiles that would escape from warmer regions are trapped in the growing icy bodies. Noble gases like argon and neon, which almost never form chemical compounds, can be physically trapped in ice structures when temperatures are low enough. These temperature zones are not sharp boundaries but gradual transitions. The exact temperatures depend on many factors, including the luminosity of the central star, the density and opacity of the disk material, and the presence of other heat sources like radioactive decay of short-lived isotopes or shock heating from spiral density waves in the disk. But the general pattern holds. Distance from the star determines temperature, and temperature determines which compounds can condense into solids. The process of building a comet begins with dust grains. These microscopic particles, typically less than a micrometer in size, are the seeds around which larger bodies grow. In the cold outer regions of the protoplanetary disk, water vapor and other volatiles condense onto these dust grain surfaces, coating them with layers of ice. The ice-coated grains stick together when they collide at low velocities, a process called accretion. Unlike high-speed impacts that shatter objects, gentle collisions at speeds of millimeters per second or less allow grains to merge through a combination of electrostatic forces, van der Waals forces, and the natural stickiness of ice. As grains accrete into larger aggregates, the growing bodies sweep up more material from their surroundings. Objects that reach sizes of centimeters or meters have enough cross-sectional area to collect substantial amounts of dust and ice over millions of years of growth, but they also face new challenges. As they grow larger, their orbital velocities relative to the surrounding gas become more pronounced. The gas in the protoplanetary disk orbits slightly slower than solid particles would in pure Keplerian orbits, because gas pressure provides additional support against gravity. This velocity difference creates drag on solid particles, causing them to gradually spiral inward toward the star. This radial drift is a major problem for building large bodies in protoplanetary disks. Objects that grow to sizes of meters or kilometers experience significant drag and can migrate inward rapidly on astronomical timescales, potentially reaching the inner system and being destroyed before they can grow further. The fact that comets and planets exist at all suggests that some mechanism must allow rapid growth through this dangerous size range. Possible solutions include turbulence in the disk that concentrates particles into dense clumps where rapid accretion can occur, or the formation of pressure bumps in the disk where solid particles accumulate and can grow efficiently. Once bodies reach sizes of tens of kilometers, their own gravity becomes significant. At these sizes, they can begin attracting smaller objects gravitationally, rather than relying purely on random collisions. This gravitational focusing accelerates growth, allowing the largest bodies to sweep up material from wide regions around their orbits. In the inner solar system, this process led to the formation of planetary embryos that eventually became the terrestrial planets. In the outer system, it created the cores of the giant planets and the population of large bodies we now call dwarf planets, Kuiper belt objects, and the precursors of long-period comets. But many bodies never grew large enough to become planets. They remained as relatively small objects, anywhere from a few hundred meters to a few hundred kilometers across, scattered throughout the outer solar system. These are the comets and trans-Neptunian objects that preserve a record of the disk's original composition. Because they formed in the cold outer regions and never experienced significant heating, they retained the volatile ices that condensed from the protoplanetary nebula. They are, in a very real sense, frozen samples of the solar nebula. The chemical composition of these ices reflects the temperature and pressure conditions where they formed. Water ice, the most abundant volatile in most comets, condensed over a wide range of temperatures and is found in objects that formed anywhere beyond about 3 astronomical units. Carbon dioxide ice, which requires lower temperatures, is more abundant in objects that formed beyond 10 or 15 astronomical units. Carbon monoxide, requiring even colder conditions, is typically found in comets that formed in the outermost regions of the disk, or that incorporated material from the pre-solar molecular cloud that had never been fully vaporized during disk formation. The deuterium to hydrogen ratio in water ice provides a sensitive thermometer for formation conditions. Deuterium, the heavy isotope of hydrogen, is slightly more readily incorporated into ice molecules than normal hydrogen when temperatures are very low. By measuring the DH ratio in cometary water, astronomers can estimate the temperature at which that water ice originally condensed. Comets with high DH ratios formed in very cold environments, possibly in the outer reaches of the protoplanetary disk, or even in interstellar space before the solar system formed. Those with lower DH ratios formed in warmer regions closer to the star. This chemical diversity explains why different comets show different compositions when observed spectroscopically. A comet that formed at 20 astronomical units in a region where temperatures were around 50 Kelvin will have different ice ratios than one that formed at 40 astronomical units where temperatures were 30 Kelvin. And both will differ from comets that incorporated interstellar ices that formed at temperatures below 20 Kelvin in the pre-solar molecular cloud. For interstellar comets like 3I Atlas, the situation is more complex because we don't know where in their original protoplanetary disk they formed. We don't know what type of star they orbited or what that star's luminosity was. A comet that formed at 20 astronomical units around a dim red dwarf might have experienced temperatures of 30 Kelvin because red dwarfs are so cool and emit so little light. The same distance around a bright star like our Sun might correspond to 50 or 60 Kelvin. So the chemical composition alone doesn't tell us the formation distance unless we also know the central star's properties. But the composition does tell us about the chemical environment. The carbon dioxide dominance that James Webb detected in 3I Atlas suggests formation in a region where CO2 could condense efficiently. This requires temperatures below about 70 Kelvin, but above about 25 Kelvin, where carbon monoxide would dominate instead. The presence of nickel vapor, while not directly informative about formation temperatures since the nickel is vaporizing now rather than being primordial, does indicate that the comet contains minerals with unusual composition or structure that allow metal vaporization under conditions where it shouldn't normally occur. These clues, fragmentary as they are, allow us to piece together a rough picture of 3I Atlas's birth environment. It probably formed in the outer regions of a protoplanetary disk, beyond the snowline where water ice was stable, but not in the most extreme outer reaches where carbon monoxide would dominate. The parent star was probably not a very hot luminous star because those create warmer disks that wouldn't allow CO2-dominated ices. But it wasn't necessarily a very cool dim star either, because 2I Borisov, which showed very high carbon monoxide, is the better candidate for a red dwarf origin. More likely, 3I Atlas formed around a star somewhat similar to our Sun, perhaps slightly cooler, or in a region of the disk that was more carbon dioxide rich than our solar system's formation zones. The age estimates of 3 to 11 billion years suggest the comet could have formed around an old star from an earlier generation of the galaxy's stellar population, when the overall metallicity of the interstellar medium was different from today. Metallicity, in astronomical terms, refers to the abundance of elements heavier than hydrogen and helium. The first stars that formed in the universe, population 3 stars, contained only hydrogen and helium because no heavier elements existed yet. These stars lived, died, and ejected processed material through supernovae, enriching the interstellar medium with carbon, oxygen, nitrogen, silicon, iron, and other elements. Subsequent generations of stars formed from this enriched material and were thus more metal-rich. The process continues, with each stellar generation slightly increasing the average metallicity of the galaxy. Our Sun is a relatively young star, only about 4.6 billion years old, and formed from material that had been through many cycles of stellar processing. Its metallicity is fairly high compared to the galactic average, but 7 to 11 billion years ago, when 3I Atlas may have formed, the galaxy's overall metallicity was lower. Stars forming then would have had less iron, less silicon, less of the heavy elements that make up rocky planets, and the mineral grains in comet nuclei. This lower metallicity might explain some of the unusual properties of 3I Atlas if its composition reflects a different balance of elements than solar system comets formed from. But formation is only the beginning of a comet's story. After the initial accretion phase, after the protoplanetary disk dissipates and planet formation is mostly complete, comets face billions of years of evolution that can alter their properties substantially. Radiation processing is one of the most important evolutionary mechanisms. In the cold outer regions where comets reside, temperatures are far too low for chemical reactions to proceed at appreciable rates through thermal processes. But cosmic rays, high-energy particles accelerating through the galaxy, constantly bombard all objects in space. When these energetic particles strike molecules in cometary ices, they can break chemical bonds and create reactive species that recombine in new ways. The result, over millions and billions of years, is the gradual accumulation of complex organic molecules. Simple molecules like water, carbon dioxide, and methane are transformed into more complex species. Formaldehyde forms from water and carbon monoxide. Methanol forms from methane and oxygen atoms. Larger organic molecules, chains and rings of carbon atoms with various functional groups attached, build up slowly through this radiation chemistry. The reddish-brown tholins detected on 3I Atlas's surface are products of exactly this process. Tholin is a generic term for complex organic solids produced by radiation or ultraviolet light processing of simpler molecules. The exact chemical structure of tholins is highly variable depending on the starting materials and the type of radiation exposure, but they typically consist of long polymer chains with carbon-carbon and carbon-nitrogen bonds. Their reddish-brown colour comes from their optical properties, absorbing blue light more strongly than red light, and thus appearing reddish when viewed in reflected sunlight. The presence of tholins on an interstellar comet tells us that the object has spent a very long time exposed to cosmic radiation in the interstellar environment. Calculating the exact exposure age from the Tholin abundance requires knowing the flux of cosmic rays, the shielding provided by overlying material, and the efficiency of Tholin formation under interstellar conditions. But rough estimates suggest that developing the thick Tholin layers observed on objects like 3I Atlas requires hundreds of millions to billions of years of exposure. This radiation processing doesn't just create complex organics on the surface, it also affects the deeper interior, though more slowly because cosmic rays must penetrate through overlying material to reach deeper layers. The most energetic cosmic rays can penetrate meters or even tens of meters into a cometary nucleus, gradually processing the ices throughout a substantial fraction of the interior volume. But the very deepest interior, the core of the nucleus, may remain pristine and unprocessed, preserving the original composition from formation. When a comet approaches the Sun, after billions of years in cold storage, the outer processed layers sublimate first, releasing the complex organics and altered ices. But as the comet continues to outgas, deeper and less processed layers become exposed. If observations could track compositional changes as different layers sublimate, they might reveal a chemical stratigraphy showing how radiation processing varied with depth. Another evolutionary process is collisional modification. Space is not truly empty. Even in the interstellar void, objects occasionally encounter each other. The probability of a collision is low for any individual object over short timescales, but over billions of years, even unlikely events become probable. An interstellar comet drifting through the galaxy for 5 billion years travels roughly 5,000 light-years if it's moving at a typical interstellar velocity of about 1 kilometer per second. During that journey, it passes through numerous regions of differing dust densities, possibly traverses molecular clouds, and may experience occasional close encounters with stellar systems. Each encounter with a dense molecular cloud subjects the comet to enhanced dust bombardment as it plows through the cloud's gas and small particles. These tiny impacts gradually sandblast the surface, eroding material and potentially exposing fresh subsurface layers. Larger impacts from kilometer-sized objects are rarer, but can have more dramatic effects, potentially fracturing the nucleus or even breaking it into multiple pieces. The tumbling rotation states of interstellar objects like Oumuamua and probably 3I Atlas are signatures of collisional history. A freshly formed comet ejected from its parent system likely has a fairly regular rotation state reflecting the conditions of its ejection. But random impacts over billions of years impart angular momentum in different directions, causing the rotation axis to precess and the spin rate to change unpredictably. By the time the object encounters another stellar system, its rotation state has been randomized by countless small impacts. Gravitational encounters with stars and stellar systems also modify interstellar comet trajectories and potentially their physical properties. When an interstellar object passes through a stellar system, the star's gravity bends its trajectory, changing the object's direction and speed. If the encounter is close enough, tidal forces can stress the object's structure, potentially causing fractures or triggering outbursts if the tidal forces are strong enough to breach barriers containing pressurized subsurface volatiles. These various evolutionary processes, radiation processing, collisional modification, occasional stellar encounters, mean that the 3I Atlas we observe today is not the same object that formed billions of years ago. Its surface has been altered by radiation. Its interior may be fractured by impacts or tidal encounters. Its rotation state has been randomized. And yet, despite all these changes, the object still preserves information about its formation conditions in its bulk composition and internal structure. Disentangling what's primordial from what's evolutionary requires careful analysis and comparison with other objects. If all interstellar comets from old stellar populations show similar surface colours that suggest the Tholins are genuine products of long-term radiation exposure rather than primordial features, If some interstellar comets show very different compositions despite similar ages, that suggests compositional diversity was present at formation rather than being created by evolutionary processes. This is why detecting and studying many interstellar objects is so important. 1 or 3 objects can't reveal patterns, but dozens or hundreds can. With a large sample, statistical analysis can separate primary features that reflect formation conditions from secondary features that result from billions of years of evolution in interstellar space. The history of comet discovery and observation provides context for appreciating how far our capabilities have advanced. For most of human history, comets were mysterious and frightening apparitions. They appeared unpredictably in the night sky, grew bright over days or weeks, displayed spectacular tails, and then faded away. No pattern was apparent, no prediction was possible. They seemed to violate the orderly celestial mechanics governing the sun, moon, planets, and stars. Ancient cultures developed elaborate mythologies around comets. Some saw them as omens of disaster, harbingers of war, famine, or the deaths of kings. Others viewed them as messages from gods or ancestors. Chinese astronomers maintain detailed records of comet observations dating back more than 2,000 years, cataloguing their appearances and searching for patterns, even if the underlying physics remained mysterious. The first scientific breakthrough came from Tycho Brahe in 1577. When a bright comet appeared that year, Tycho made careful positional measurements from his observatory on the island of Hven. By comparing his observations with those made by other astronomers at different locations, he could use the principle of parallax to determine that the comet was much farther away than the Moon. This was revolutionary because Aristotelian philosophy held that comets were atmospheric phenomena, burning gases in the upper air below the sphere of the Moon. Tycho proved that comets were truly celestial objects, participants in the cosmic dance rather than mere atmospheric effects. Isaac Newton's work in the late 1600s provided the next major advance. By demonstrating that gravity governed the motions of both planets and comets according to the same mathematical laws, Newton transformed comets from unpredictable omens into objects following calculable orbits. His Principia Mathematica included calculations showing that the comet of 1680 followed a parabolic trajectory around the Sun, proving that comets orbited our star just as planets did, though on much more elongated paths. Edmund Halley applied Newton's methods to historical comet observations and made his famous prediction that the comets of 1531, 1607, and 1682 were the same object returning periodically. When the comet reappeared in 1758 as Halley predicted, it validated both Newton's gravitational theory and the idea that at least some comets were permanent members of the solar system rather than one-time visitors. The 18th and 19th centuries saw steady improvements in comet discovery and orbit calculation. Telescopes allowed detection of fainter comets that were invisible to the naked eye. Better mathematical methods for calculating orbits from positional observations made predictions more reliable. Catalogues of known comets grew and patterns began to emerge. Some comets returned regularly on periods of years or decades. Others appeared once and vanished on parabolic or hyperbolic trajectories that would never bring them back. Photography revolutionized comet discovery in the late 19th century. Instead of relying on observers to visually scan the sky, astronomers could take long exposure photographs that recorded faint objects invisible to the eye. Comets moving against the background stars would appear as streaks or fuzzy patches in images taken hours or days apart. This dramatically increased the discovery rate. Comets that would have gone unnoticed in visual surveys were caught by the unblinking eye of the camera. The 20th century brought spectroscopy, allowing chemical analysis of comet comas. Instead of merely knowing that comets released gas and dust, astronomers could identify specific molecules. Water, cyanogen, carbon monoxide, sodium, and many other species were detected through their characteristic emission lines. These spectroscopic observations revealed that comets were not just dirty snowballs, as Fred Whipple's model suggested, but complex chemical factories where solar ultraviolet light drove reactions producing radicals and molecules not normally stable under terrestrial conditions. Spacecraft missions provided the first close-up views of cometary nuclei. The armada of spacecraft that flew past Halley's Comet in 1986, including Europe's Giotto probe, revealed the nucleus to be far darker and more irregular than expected. The successful Deep Impact mission in 2005, which deliberately crashed a copper impactor into Comet Tempel 1 and analysed the ejected debris, showed that cometary interiors are heterogeneous mixtures of ice and dust rather than uniform compositions. The Rosetta mission, which orbited Comet 67P Churyumov-Gerasimenko from 2014 to 2016 and deployed the Philae lander onto its surface, provided unprecedented detail about cometary geology, composition, and activity. Rosetta revealed that the comet's surface was far more complex than anticipated, with cliffs, boulders, smooth plains, and active pits where fresh ice was exposed and sublimating. The mission detected organic molecules far more complex than previously known in cometary material, including glycine, an amino acid that's a building block of proteins. But even with all these advances, interstellar comets remained purely theoretical until 2017. Astronomers had predicted they should exist. Models suggested that planetary system formation involved ejecting large amounts of material into interstellar space. Statistical calculations estimated that dozens of interstellar objects should pass through the inner solar system every year, but none had ever been definitively identified. The problem wasn't that they weren't there. The problem was detection. Interstellar objects move faster than solar system objects because they're not gravitationally bound to the sun. Their typical velocities are tens of kilometers per second, fast enough to cross the inner solar system in just a few months. Unless you catch them during that brief passage, they're gone forever. And because they're small and dark, they're only visible when fairly close to the Sun and Earth, further narrowing the observational window. What changed in 2017 was the Pan-STARRS survey telescope in Hawaii coming online with sufficient sensitivity and sky coverage to detect faint, fast-moving objects. Pan-STARRS scans large areas of sky repeatedly, looking for anything that changes or moves. This automated survey approach dramatically increases the detection rate for unusual objects because human observers can't possibly scan enough sky fast enough to catch rare fast movers. When Pan-STARRS detected Oumuamua on October 19, 2017, the initial assumption was that it was just another asteroid or comet. But as more observations came in and astronomers calculated the orbit, they realised this object was moving too fast. Its orbital eccentricity was greater than 1, meaning the orbit was hyperbolic rather than elliptical. This object wasn't bound to the Sun. It came from interstellar space and would return to interstellar space after swinging past the Sun. The realization that we had detected our first interstellar visitor caused immediate excitement and scramble for observations. Every available telescope that could reach the object was pointed at it. Spectroscopy was attempted but proved difficult because the object was already receding and fading rapidly. Within weeks, it had become too faint for detailed study. By the time astronomers fully appreciated what they were seeing, Oumuamua was already leaving, and the opportunity for comprehensive observations had passed. The experience with Oumuamua taught the astronomical community crucial lessons. When the next interstellar visitor was detected, they would be prepared. Networks were established to rapidly disseminate information about new discoveries. Protocols were developed for fast response observations. Telescope time was pre-allocated for targets of opportunity that might appear with little warning. When 2I Borisov was discovered in August 2019 by Crimean amateur astronomer Gennady Borisov, the response was swift and coordinated. Within days, dozens of telescopes were observing the comet. Within weeks, comprehensive spectroscopy had been obtained. By the time it reached perihelion in December 2019, astronomers had amassed more data on Borisov than was ever obtained for Oumuamua. The comet remained observable for months, allowing detailed study of its evolution as it warmed approaching the Sun and cooled receding afterward. The discovery of 3I Atlas in July 2025 benefited from this established infrastructure. The Atlas survey that detected it was specifically designed to find fast-moving objects. The rapid orbit determination and confirmation of interstellar origin allowed months of preparation before perihelion. The coordination with Mars orbiters for the October 3rd flyby represented unprecedented multi-platform observation of an interstellar visitor. But there's always room for improvement. The high-rise data delay revealed that bureaucratic systems haven't fully caught up with the scientific imperatives of rapid data sharing for time-critical targets. The difficulty in getting comprehensive spectroscopy before the comet became too active showed that allocating telescope time for unpredictable targets remains challenging. And the limited opportunities for close observation reminded everyone that we need better systems for intercepting these visitors before they pass us by. The future of interstellar object detection depends heavily on the Vera C. Rubin Observatory. This facility, currently being commissioned in Chile, represents a revolution in time-domain astronomy. Its 8.4-meter primary mirror is large enough to reach faint objects, while its 3.5-degree field of view is wide enough to scan vast areas of sky quickly. The combination of large aperture and wide field is unusual. Most large telescopes have narrow fields optimized for deep observations of small regions. Rubin is designed for wide area surveying, imaging the entire visible sky every few nights. The technical specifications are impressive. The camera contains 3.2 billion pixels, arranged in 189 individual charge-coupled device sensors. Each sensor is a marvel of engineering, designed to operate with extremely low noise and high quantum efficiency across a wide wavelength range. The entire camera is cooled to minus 100 degrees Celsius to reduce thermal noise. The data rate will be enormous, roughly 15 terabytes of raw imaging data every night. Processing this data stream to detect moving objects and transient events requires sophisticated software pipelines and substantial computing resources. When Rubin begins full operations, it should detect interstellar objects routinely. Conservative estimates suggest one per month. More optimistic projections, assuming interstellar object populations are at the high end of plausible ranges, suggest several per week. Even the conservative estimate would mean dozens per year, transforming interstellar visitors from rare events studied intensively to common events requiring triage and selective detailed follow-up. This abundance creates new challenges. With dozens or hundreds of interstellar objects detected, which ones deserve expensive follow-up spectroscopy on the largest telescopes? Which ones are scientifically most valuable? The brightest ones are easiest to study, but might not be the most interesting compositionally. Objects with unusual trajectories, perhaps passing very close to planets or the Sun, offer unique opportunities but may be harder to observe due to geometric constraints. Developing selection criteria will require community consensus and probably some trial and error as we learn which types of observations yield the most valuable science. Do we prioritize spectroscopy of the brightest objects to get the highest signal-to-noise data? Or do we spread observations across many objects to sample diversity? Do we focus on comets with active comas that reveal composition through outgassing? Or on apparently inactive objects that might be more asteroid-like? These questions don't have obvious answers yet because we're still in the early phases of interstellar object astronomy. In 10 years after detecting and studying hundreds of these objects, the community will have much better understanding of which observational strategies are most productive. But for now, every detection is still novel enough that it receives substantial attention. Beyond detection and characterization, the ultimate goal is direct exploration. Several mission concepts have been proposed for intercepting and studying interstellar visitors up close. The European Space Agency's Comet Interceptor mission, currently under development, is designed to wait in space at the Earth-Sun L2 Lagrange point until a suitable target appears, then rapidly deploy to intercept the object during its passage through the inner solar system. This mission concept represents a fundamentally different approach from traditional planetary missions. Normally, spacecraft are designed and built for specific predetermined targets. Comet Interceptor will launch without knowing which object it will eventually study. The spacecraft will wait on station, ready to respond when a promising target is identified. This requires designing the mission to be flexible enough to handle a range of possible target properties while still optimizing performance for the most likely scenarios. The spacecraft design includes 3 separate modules. A primary spacecraft will perform remote sensing observations as it approaches the target. 2 smaller probes will separate from the main craft and fly past the target from different directions, providing multiple viewing geometries and in situ measurements of the coma environment. The multi-probe approach maximizes science return and provides redundancy in case one probe experiences problems. Launch is currently scheduled for 2029, with the spacecraft then waiting at L2 for a suitable target to appear. Depending on detection rates and target selection criteria, it might wait months or years before deploying. But once a target is identified and the go-ahead given, the spacecraft can reach its target within weeks or months depending on the object's trajectory and the available Delta-V budget. Comet Interceptor is just the first of what will hopefully be many missions to interstellar visitors. More ambitious concepts include sample return missions that would collect material from an interstellar comet's coma and return it to Earth for detailed laboratory analysis. Such missions are technically challenging because matching velocities with a fast-moving interstellar object requires substantial propulsion capability. But the scientific payoff would be enormous. Analysing pristine material from another stellar system in terrestrial laboratories, with instruments far more sophisticated than can be flown in space, would reveal details about chemistry and mineralogy that remote observations can never provide. Even more ambitious are concepts for rendezvousing with and landing on an interstellar object's nucleus. This would require not just intercepting the object, but matching velocities well enough to maintain position relative to the surface. The challenges are substantial. The object's rotation state is likely irregular, making landing site selection difficult. The surface properties are unknown, potentially too soft to support a lander, or too hard to allow anchoring. The thermal environment during approach to the Sun could stress spacecraft systems, and communication with Earth becomes challenging as the object and spacecraft recede into the outer solar system. But despite these challenges, such missions are not beyond current technological capabilities. We've landed on asteroids and comets before. Rosetta's Philae lander touched down on Comet 67P. OSIRIS-REx collected samples from asteroid Bennu. The Hayabusa and Hayabusa 2 missions returned samples from asteroids Itokawa and Ryugu. Adapting these techniques to interstellar targets adds complications, but doesn't require fundamentally new technologies. The propulsion requirements are perhaps the most challenging aspect. Interstellar objects are moving fast, typically 20 to 40 kilometers per second relative to the Sun. Matching that velocity requires a spacecraft with substantial Delta-V capability. Traditional chemical propulsion struggles with these requirements. Electric propulsion systems like ion drives can provide the necessary velocity changes but require long thrust times, potentially years of continuous acceleration. More exotic propulsion systems have been proposed. Solar sails, which use momentum from sunlight to accelerate spacecraft, could potentially reach high velocities if deployed close to the Sun where light is intense. Nuclear thermal propulsion, which heats reaction mass using a nuclear reactor rather than chemical combustion, could provide higher specific impulse than chemical rockets. Fusion propulsion, still purely theoretical but potentially capable of providing enormous thrust and efficiency, might eventually enable rapid interception of even the fastest interstellar visitors. Near-term missions will likely rely on conventional propulsion, with gravity assists and clever trajectory design to minimize fuel requirements. But as propulsion technology advances, more ambitious missions become possible. Perhaps within a century we'll have spacecraft capable of intercepting any interstellar object that passes through the inner solar system and conducting comprehensive in situ studies before the object departs. The long-term vision extends even further. If interstellar objects are as common as detection rates suggest, they provide a potential resource for future spacefaring civilizations. An object several kilometers across contains billions of tons of material, primarily water ice but also rock, metals, and complex organic compounds. This material could support industrial processes in space, provide propellant and life support consumables for long-duration missions, or even be carved into habitats for human habitation. This vision of utilizing interstellar objects might seem far-fetched given our current technological capabilities, but it's worth remembering that a century ago landing on the moon seemed equally impossible. Technologies advance. What seems far-fetched today often becomes routine tomorrow. The interstellar objects passing through our solar system represent not just scientific opportunities, but potential resources that future generations might exploit. But even without grand visions of resource utilization, the scientific value of studying these cosmic wanderers is clear. Each one is a sample from a different stellar environment. Each one carries information about planetary system formation under conditions we can't study any other way. Each one expands our understanding of what's possible in the galaxy. And beyond the scientific value, there's something profound about the fact that we can now detect and study visitors from other stellar systems. For billions of years, these objects have been silently drifting through the galaxy, occasionally passing through stellar systems, but going unnoticed by any observers. Now, for the first time, a species has developed the technology to recognize them for what they are and study them systematically. We are witnessing the birth of a new field of astronomy. Interstellar object science is only 8 years old, dating from Oumuamua's detection in 2017. In astronomical terms, that's no time at all, and yet already we've detected 3 confirmed visitors, developed systematic observation strategies, launched missions designed to intercept future visitors, and begun building theoretical frameworks for understanding the populations and properties of galactic debris. Imagine where this field will be in another decade, or a century. The detection rates will increase dramatically as new facilities come online. The observation techniques will improve as we learn which measurements are most informative. Missions will return samples, and perhaps eventually allow human researchers to examine interstellar material directly. Theories will mature as data accumulates and patterns emerge, and through it all, the fundamental mystery remains. Where do these objects come from? What stellar systems birthed them? What processes ejected them into the cosmic void? How many are out there, drifting through the galaxy, waiting to be discovered? These questions drive the field forward. Every detection provides new data. Every observation refines our understanding. Every mission brings us closer to comprehensive knowledge of the galactic environment that surrounds our tiny solar system. 3i Atlas, with all its anomalies and surprises, is one step on this journey. It has taught us lessons we needed to learn. It has revealed phenomena we didn't anticipate. It has challenged our assumptions and forced us to think more deeply about cometary physics and galactic chemical evolution. But it's not the end. It's barely the beginning. The journey continues, observation by observation, discovery by discovery. And somewhere out there, right now, the next interstellar visitor is approaching. We don't know when it will arrive or what it will reveal, but when it comes, we'll be ready. We'll point our telescopes toward it. We'll gather every photon we can. We'll analyze the data carefully and extract every piece of information those photons carry. Because that's what we do. We observe, we study, we learn. One cosmic visitor at a time, we expand the boundaries of human knowledge and deepen our understanding of the galaxy we inhabit. The story continues, the observations accumulate, and slowly, patiently, The universe reveals its secrets to those who pay attention. This is the work. This is the calling. This is humanity's contribution to the cosmos, bearing witness to its wonders and recording what we see for future generations who will carry the work forward long after we're gone. The comet fades, the data remains, the knowledge grows, and the journey continues, deeper into cosmic understanding, one observation at a time.